In the quiet corners of materials science laboratories around the world, there exists a substance so remarkable, so extraordinary in its properties, that it has earned a name whispered with reverence among engineers and scientists alike. They call it the black diamond. But this is no gemstone pulled from the earth by miners seeking fortune. This is something different, something engineered, something that would change the very nature of protection and defense in our modern world. Let us begin our journey into the heart of this mysterious material by understanding what it truly is. Boron carbide. The name itself sounds technical, almost cold. But within those two simple words lies a universe of atomic precision and chemical elegance. Its formula, B4C, tells us that this material is composed primarily of just two elements, boron and carbon. For atoms of boron, bound together with one atom of carbon, repeating endlessly in a crystalline lattice of extraordinary strength. Think about that for a moment. Just two elements. Boron, a metalloid that sits quietly in the periodic table, often overlooked, rarely celebrated. And carbon, the very foundation of life itself, the element that forms the graphite in your pencil and the diamond in an engagement ring. These two elements, when brought together under the right conditions, create something that defies our everyday understanding of materials. But what makes boron carbide so special? Why does it deserve this dramatic nickname, this comparison to diamond itself? The answer lies in a property that humans have valued since the dawn of toolmaking: hardness. Hardness is not just about being difficult to scratch, though that's certainly part of it. Hardness represents a material's ability to resist deformation, to maintain its shape and integrity when other materials would yield, would bend, would break. Throughout human history, the hardest materials have been the most prized. From flint used by our ancient ancestors to shape the first tools, to the diamonds we use today to cut through nearly anything. And boron carbide. Boron carbide has earned a place among the elite few materials that sit at the very pinnacle of hardness. This extreme hardness, this resistance to deformation, and earned boron carbide its evocative nickname, black diamond. When scientists and engineers first began working with this material, when they first tested its properties and witnessed what it could do, they needed a way to communicate its remarkable nature. And what better comparison than diamond itself? Diamond, the hardest naturally occurring substance known to humanity. Diamond, the material by which all other hard materials are measured. But where does boron carbide actually rank in this hierarchy of hardness? Let us consider the champions of hardness in the materials world. At the very top sits diamond, pure carbon, arranged in a cubic crystal structure of breathtaking perfection. Nothing is harder than diamond. It is the ultimate, the peak, the reference point for all comparisons. Just below diamond sits cubic boron nitride, often abbreviated as CBN. This synthetic material, like diamond, possesses extraordinary hardness, and it's often used in industrial applications where diamond might react unfavorably with certain metals. And then comes boron carbide. Boron carbide ranks just behind diamond and cubic boron nitride in hardness. Think about that placement. In a world of countless materials, metals, ceramics, polymers, composites, boron carbide claims the third position. Bronze medal in the Olympics of hardness. But unlike the Olympics, where the difference between gold and bronze might be mere hundredths of a second, the gap between ordinary materials and these top three is vast, almost incomprehensible. To put numbers to this remarkable hardness, scientists often turn to the Mohs scale, a measurement system you might remember from geology class, where diamond sits at 10 and talc, soft enough to scratch with your fingernail, sits at 1. On the Mohs scale, boron carbide measures approximately 9.5 to 9.75. Let that sink in for a moment. If diamond is 10, the maximum, boron carbide approaches it incredibly closely. The difference is minimal. And yet, that difference matters greatly in the absolute sense, because the Mohs scale is not linear. Each step up represents a significant leap in actual hardness. But the Mohs scale, useful as it is, tells only part of the story. It's a relative scale, a ranking system. For more precise measurements, scientists turn to something called Vickers hardness, a test where a diamond pyramid is pressed into a material under a specific load, and the size of the indentation is measured. When subjected to Vickers hardness testing, boron carbide typically shows values reaching between 28 and 38 gigapascals, abbreviated as GPa. Let's pause and consider what a gigapascal means. Pascal is a unit of pressure, specifically 1 Newton of force applied over 1 square meter. A gigapascal is 1 billion pascals. To achieve 28 to 38 GPa of Vickers hardness means that boron carbide can withstand extraordinary forces concentrated into the tiny pyramid-shaped tip of a diamond indenter without permanently deforming by more than a microscopic amount. For comparison, hardened steel, the kind used in tools and machinery, might measure around 7 to 10 GPa. Common glass sits around 5 to 6 GPa. Boron carbide's 28 to 38 GPa places it in a category so far beyond ordinary materials that the comparison almost seems unfair. But hardness is not the only characteristic that defines boron carbide. There is something else, something immediately apparent to anyone who has ever held a piece of this remarkable material in their hand. Its color. Boron carbide is dark, profoundly dark. Its hue ranges from black to a deep, somber gray, the color of storm clouds, of charcoal, of midnight without stars. This darkness is not superficial, not merely a surface treatment or coating. The dark black to gray color comes from strong light absorption within the material itself. Think about what that means. When light strikes boron carbide, most of it doesn't reflect back to your eyes the way it would from a mirror or a polished metal. Instead, the light is absorbed, drawn into the atomic structure, its energy dissipated. This gives boron carbide its characteristic appearance: dark, matte, almost consuming the light around it. There's something almost poetic about this, isn't there? A material of such extraordinary strength, such remarkable hardness, presenting itself not with the brilliant sparkle of diamond, but with a quiet, understated darkness. Where diamond catches the light and throws it back in prismatic glory, boron carbide simply absorbs, remaining mysterious, hidden, revealing nothing of its inner strength through its appearance alone. This dark material, this black diamond, belongs to a special classification in the world of materials science. It's sometimes classified as an ultra-high temperature ceramic. That term, ultra-high temperature ceramic, tells us something crucial about boron carbide's nature. Ceramics, in the technical sense, are inorganic, non-metallic materials that are typically crystalline and made by heating and cooling. We think of ceramics as pottery, as bathroom tiles, as the plates we eat from. But advanced ceramics, and especially ultra-high temperature ceramics, are something entirely different. Ultra-high temperature ceramics are materials that can maintain their structure and properties at temperatures that would melt most metals, that would turn stone to liquid, that would challenge the very notion of solid matter. These are materials designed for the most extreme environments imaginable: rocket nozzles, hypersonic vehicle surfaces, furnace linings in the most demanding industrial processes. And boron carbide is among them. How extreme can the temperatures be? Consider this. Boron carbide's melting point can exceed 3,000 degrees Celsius. 3,000 degrees Celsius. Let's put that in perspective. Water boils at 100 degrees Celsius. Most cooking ovens reach perhaps 250 degrees. Steel melts around 1,400 to 1,500 degrees. Gold melts at 1,064 degrees. Titanium, that wonder metal of aerospace engineering, melts at 1,668 degrees. And boron carbide? It remains solid, maintaining its structure, well past 3,000 degrees Celsius. At temperatures where almost every other material would have long since turned to liquid or vapor, boron carbide endures. It persists. It maintains its integrity. Imagine that for a moment. Imagine a substance that could sit in temperatures that would vaporize most metals, and it would simply remain unchanged, unyielding, waiting patiently for the temperature to drop. But here's something fascinating. something almost contradictory about boron carbide. For all its extraordinary properties, its extreme hardness, its resistance to incredible temperatures, its remarkable density and strength. When you look at it, when you hold a piece in your hand, despite its hardness, it looks unassuming, almost dull. There is no flash, no glamour, no immediate visual indication that you're holding one of the most remarkable materials ever created by human ingenuity. It doesn't shine like polished steel. It doesn't gleam like silver or gold. It doesn't sparkle like diamond. It simply sits there, dark and matte, looking for all the world like a chunk of particularly dense charcoal or a piece of dark, fired clay. An engineer unfamiliar with boron carbide could walk past a piece sitting on a workbench and never give it a second glance. It demands no attention. It makes no grand claims through its appearance. In a world where we often judge materials by their visual appeal, where we admire the gleam of chrome, the luster of polished wood, the transparency of fine glass, boron carbide simply refuses to participate in that aesthetic competition. And yet it would become one of the most important armor materials ever made. This unassuming black to grey ceramic, this black diamond, that looks like nothing special to the untrained eye, would prove itself on battlefields and in protection systems around the world. It would save lives. It would stop projectiles that would pass through steel like paper. It would become the guardian material of choice for those who face the most extreme threats. Body armor worn by soldiers, vehicle armor protecting crews, aircraft protection systems, specialized security applications. In all these contexts and more, boron carbide would prove its worth not through its appearance, but through its performance, through its ability to do what other materials simply could not do. There's something profound in this contrast between the humble appearance and the extraordinary capability. It reminds us that true strength doesn't always announce itself, that the most powerful materials, like the most capable people, sometimes present themselves quietly, without fanfare, waiting for the moment when their true nature will be revealed through action rather than appearance. As we continue our journey into the world of boron carbide, as we explore how this material is made, how it functions, and why it has become so crucial to modern armor systems, keep this image in mind: a dark, unassuming piece of ceramic that contains within it properties that push the very boundaries of what materials can achieve. This is boron carbide. This is the black diamond. And its story is just beginning. In the world of materials engineering, there exists a persistent challenge, a puzzle that has occupied the minds of designers and scientists for generations. It is a challenge that becomes especially acute when we turn our attention to protection, to armor, to the materials we use to shield the vulnerable from harm. The challenge is this: how do you create something strong enough to stop a threat, without making it so heavy that it cannot be carried? How do you achieve strength without sacrificing mobility? How do you protect without burdening? This is the fundamental dilemma of armor design. And it is here, in addressing this ancient problem, that boron carbide reveals itself as something truly extraordinary. Let us begin with a number, a simple measurement that tells us something profound about the nature of this material. Boron carbide's density is only 2.5 to 2.52 grams per cubic centimeter. Now, perhaps you're thinking, what does that actually mean? What does density tell us? And why does this particular number matter so much? Density is the measure of how much mass is packed into a given volume. It's the reason why a cubic inch of gold feels so much heavier in your hand than a cubic inch of aluminum, even though they take up the same amount of space. It's why some materials sink and others float. It's why, when we're designing anything that needs to move, whether carried by a soldier, driven as a vehicle, or flown as an aircraft, every gram matters. At 2.5 to 2.52 grams per cubic centimeter, boron carbide sits in a remarkable position. To understand just how remarkable, we need to compare it to the materials it often replaces in armor applications. This density makes boron carbide far lighter than steel or tungsten alloys. Consider steel first, the traditional workhorse of armor applications for over a century. Steel, depending on its specific composition, typically has a density around 7.85 grams per cubic centimeter. That's roughly 3 times denser than boron carbide. 3 times. Think about what that means in practical terms. A plate of steel armor and a plate of boron carbide of the same dimensions. The steel plate would weigh approximately 3 times as much. And tungsten alloys? These materials, prized for their extreme density and often used in armor-defeating projectiles, can have densities exceeding 17 grams per cubic centimeter. That's nearly 7 times denser than boron carbide. Imagine you're a soldier and you need to wear protective armor. Every kilogram you carry is energy you must expend. Every extra weight is reduced mobility, increased fatigue, slower reaction time. The difference between wearing armor that weighs 15 kilograms and armor that weighs 45 kilograms isn't just a matter of discomfort. It's a matter of effectiveness, of survivability, of whether you can perform your mission. Or imagine you're designing an armored vehicle. Every kilogram of armor weight affects fuel efficiency, acceleration, maneuverability, the stress on the suspension system, the wear on the tires or tracks. There's a constant battle between protection and performance, and weight sits at the center of that battle. Boron carbide offers something precious in this context. It offers the possibility of protection without the crushing burden of weight that typically comes with it. But lightness alone would mean nothing if the material were weak, if it couldn't actually stop the threats it needs to stop. A piece of foam rubber is light, after all, but we don't make armor from it. The critical question is, does boron carbide maintain its protective properties despite its low density? The answer comes from another measurement, another property that tells us about the material's fundamental character. Boron carbide's elastic modulus is roughly 445 to 460 gigapascals, meaning it is extremely stiff. Let's pause here and understand what elastic modulus means, because it's crucial to understanding why boron carbide performs the way it does. Elastic modulus, sometimes called Young's modulus, measures a material's resistance to deformation when a load is applied to it. Think of it as a measure of stiffness. A material with a high elastic modulus doesn't bend or stretch easily. It maintains its shape under stress. When you push on it, it pushes back, resisting the deformation. At 445 to 460 gigapascals, boron carbide's elastic modulus is extraordinary. To put this in perspective, steel typically has an elastic modulus around 200 gigapascals. Aluminum sits around 69 gigapascals. Titanium, that marvel of aerospace engineering, measures roughly 110 gigapascals. Boron carbide? More than double that of steel. More than 4 times that of titanium. What this means in practical terms is that when a projectile strikes boron carbide armor, the material doesn't compress easily. It doesn't yield. It doesn't deform in the way that metals do. Instead, it resists with tremendous force. And in that resistance, in that refusal to deform, the energy of the projectile is managed in ways that lead to the projectile's defeat rather than the armor's failure. This combination, low density combined with extreme stiffness, is almost paradoxical. Usually, in the world of materials, we must make compromises. Light materials tend to be weak. Strong materials tend to be heavy. But boron carbide refuses this compromise. It insists on being both light and extraordinarily stiff. But stiffness and low weight are not the only properties that make boron carbide exceptional. There are other characteristics, other aspects of its nature that reveal themselves in different contexts, under different conditions. Boron carbide is chemically stable and insoluble in water. This might sound like a simple, almost mundane observation. After all, lots of materials don't dissolve in water. But let's think about what this means in the context of armor that must function in the real world, not in the controlled environment of a laboratory. Armor must work in jungles where humidity approaches 100%, where rain is measured in feet rather than inches. It must work in deserts where dust and sand infiltrate everything. It must work at sea, where salt spray corrodes even the most robust metals. It must work in Arctic conditions, in urban environments, in agricultural areas with fertilizers and chemicals. Chemical stability means that boron carbide maintains its properties across these diverse environments. Unlike many materials that might degrade, react, or change properties when exposed to moisture, boron carbide simply persists unchanged. And this stability extends beyond just water resistance. Boron carbide resists most acids and chemical attack. In industrial settings, in chemical processing facilities, in environments where protective materials might be exposed to corrosive substances, this resistance becomes crucial. Acids that would eat through metals, that would break down polymers, that would degrade ceramics of other types, boron carbide stands against them. Hydrochloric acid, sulfuric acid, nitric acid, the sorts of highly corrosive substances that require special handling and storage, boron carbide resists their attack. Not forever, not under all concentrations and conditions, but with a resilience that far exceeds most materials. This chemical resistance means that armor made from boron carbide doesn't require the extensive protective coatings and treatments that metal armor often demands. It can function in harsh chemical environments without degrading. It maintains its integrity not just mechanically, but chemically. But chemical stability is only one dimension of how boron carbide maintains its properties across varying conditions. There's another axis of stability that matters just as much, if not more, in armor applications. Boron carbide maintains strength across extreme temperatures. We've already discussed how boron carbide can withstand temperatures exceeding 3,000 degrees Celsius before melting. But maintaining strength across extreme temperatures means something more than just not melting. It means that the material's protective properties, its hardness, its stiffness, its ability to defeat projectiles, remain consistent whether it's experiencing Arctic cold or desert heat. Many materials become brittle at low temperatures, prone to cracking and failure. Others soften at elevated temperatures, losing the very properties that make them useful for protection. Boron carbide, remarkably, maintains its characteristics across a temperature range that spans from the coldest environments on Earth to temperatures that would melt most metals. Think about what this means for military equipment that might be deployed anywhere in the world, from the frozen expanses of the Arctic to the scorching heat of Middle Eastern deserts. The armor needs to work equally well in both environments, without adjustment, without special conditioning, without failure. And unlike metals, which often undergo significant property changes with temperature, boron carbide's ceramic nature provides remarkable stability. Its atomic structure, locked in that crystalline arrangement of boron and carbon, doesn't reorganize or phase change in the temperature ranges it's likely to encounter in service. This temperature stability connects to another crucial advantage that boron carbide holds over traditional metal armor materials. Boron carbide does not corrode like metals in field environments. Corrosion, the gradual degradation of materials through chemical reaction with their environment, is the silent enemy of metal structures everywhere. Iron rusts, aluminum forms oxide layers. Even stainless steel, in the right conditions, can corrode. Corrosion doesn't just affect appearance. It degrades material properties. It creates weak points. It reduces thickness. It introduces crack initiation sites. A piece of steel armor that corrodes has quite literally lost some of its protective capability, sacrificed to chemical reaction with oxygen and moisture. But boron carbide, as a ceramic rather than a metal, simply doesn't corrode in the same way. There's no rust, no oxidation in the destructive sense, no gradual eating away of the material. A boron carbide armor plate stored for years in a humid environment will emerge with its properties essentially unchanged, ready for service, uncompromised by time and environmental exposure. This has enormous implications for logistics, for storage, for maintenance. Military equipment often spends more time in storage than in active use. The ability to store armor components for years, even decades, without degradation is invaluable. And this resistance to environmental degradation extends to thermal conditions as well. Boron carbide does not soften under heat like traditional armor steel. Steel armor, when exposed to elevated temperatures, whether from nearby fires, from explosive events, or from sustained high-temperature environments, can lose temper, can soften, can have its carefully engineered properties compromised. A piece of hardened armor steel that experiences a fire might emerge structurally intact, but with significantly reduced protective capability, because the heat treatment that gave it its hardness has been partially undone. Boron carbide faces no such vulnerability. Its hardness, its stiffness, its protective properties are not the result of heat treatment that can be undone. They are intrinsic to its atomic structure. Heat may eventually melt it if temperatures are extreme enough, but below that melting point, the material maintains its characteristics with remarkable consistency. Consider a vehicle fire, an unfortunately common occurrence in military operations. Traditional steel armor near the fire might be compromised, might need replacement or rehardening. Boron carbide armor in the same location would emerge ready for continued service, its properties unchanged. When we step back and consider all these properties together, the chemical stability, the resistance to acids, the temperature stability, the lack of corrosion, the resistance to thermal softening, a pattern emerges. These traits make boron carbide ideal for hostile environments. And hostile environments, in this context, means more than just battlefields, though certainly those are included. It means anywhere that demands materials maintain their properties despite difficult conditions. Industrial sites, chemical processing facilities, aerospace applications, marine environments, nuclear facilities where radiation and temperature and chemical exposure all combine. Boron carbide doesn't complain. It doesn't ask for special treatment. It doesn't require constant maintenance and monitoring. It simply works, consistently, across a range of conditions that would challenge or destroy many other materials. But let's return now to where we began this segment, to that fundamental challenge of armor design, to that persistent tension between protection and weight. Throughout history, armor makers have understood a simple truth. To stop a stronger threat, you need stronger armor. And traditionally, stronger armor has meant heavier armor. The medieval knight's plate armor could stop a sword, but it weighed so much that the knight needed help mounting his horse. Early tank armor could stop small arms fire, but it was so heavy that it limited speed and range. Traditional ceramic armor could defeat rifle rounds, but it added so much weight that soldiers couldn't carry enough of it to protect their entire torso. This has been the perpetual compromise: protection or mobility. Choose one, sacrifice the other, until materials like boron carbide began to change the equation. Strength without weight is the holy grail of armor. Think about what that phrase means: strength without weight. It's an aspiration that has driven materials science for decades. It's the dream that enables new possibilities, new designs, new approaches to protection that would be impossible with traditional materials. With boron carbide, we approach that ideal. Not perfectly. There are still trade-offs, still challenges, still limitations. But we approach it more closely than ever before. A soldier can wear more comprehensive armor without being overburdened. A vehicle can be better protected without sacrificing speed and fuel efficiency. An aircraft can add armor to critical areas without the weight penalty becoming prohibitive. A civilian armored vehicle can protect occupants without requiring a massive engine just to move the armor weight. This is the promise of boron carbide: protection that doesn't demand crushing sacrifice. Defense that doesn't come at the cost of capability. In the quiet laboratories where materials scientists study this dark ceramic, where they test its properties and push its limits, they are not just studying a material. They are unlocking possibilities. They are solving problems that have challenged armor designers since humans first sought to protect themselves from harm. Boron carbide doesn't look impressive. As we noted before, it's dark, matte, unassuming. But in its atomic structure, in the arrangement of those boron and carbon atoms, in the bonds that hold them together, lies a combination of properties that continues to surprise and enable. Light but stiff, hard but stable, chemically resistant but thermally robust. protective but practical. These are the paradoxes that boron carbide embodies. These are the characteristics that make it not just another material, but a transformative one. A material that defies the expectations built up over centuries of working with metals and traditional armor materials. As we continue our exploration of boron carbide, as we delve deeper into how it's made and how it functions when faced with the ultimate test, the impact of a high-velocity projectile, keep these properties in mind. Keep this sense of paradox, of defied expectations, of a material that refuses to accept the traditional compromises. This is boron carbide, continuing to reveal its secrets, layer by layer. There is something almost magical about the way atoms arrange themselves. Given the right conditions, the right elements, the right temperatures and pressures, individual atoms will find each other and lock into patterns of extraordinary precision. These patterns, these crystalline structures, determine everything about how a material behaves, how it responds to stress, how it interacts with the world. To truly understand boron carbide, to grasp why it performs the way it does, we must journey inward. We must leave behind the world of centimeters and millimeters and travel to the realm of nanometers and angstroms, to the scale where individual atoms become visible, where structure becomes destiny. Let us begin that journey now, zooming into the material itself, past the dark surface, past the macroscopic form, down to the fundamental architecture that makes boron carbide what it is. Boron carbide has a rhombohedral crystal structure. Perhaps you're wondering, what does rhombohedral mean? What does this geometric description tell us about the material? Imagine a cube, a simple, familiar shape with 6 square faces, all edges equal, all angles 90 degrees. Now imagine taking that cube and gently stretching it along one diagonal, from one corner to the opposite corner. The cube distorts. It's no longer quite cubic, but it maintains a kind of threefold symmetry. The shape you've created is rhombohedral, a structure where the unit cell, the basic repeating pattern, has all edges equal, but angles that are not 90 degrees. In boron carbide, this rhombohedral structure manifests as a complex arrangement. The boron atoms link together forming icosahedral clusters. Imagine 12 atoms arranged as if they sat at the vertices of a 20-sided die, all connected. These icosahedral units then link together through chains that may include carbon atoms, creating a three-dimensional network of extraordinary strength. This is not a simple structure. This is not atoms stacked neatly like oranges in a crate. This is architecture at the atomic scale, where the placement of every atom matters, where the angles of every bond contribute to the whole. And this structure, this specific geometric arrangement, this is what gives boron carbide its remarkable properties. This structure contributes to its unusual hardness-to-weight ratio. Think about what hardness means at the atomic level. When something tries to scratch or indent a material, what's really happening is that forces are being applied that try to move atoms out of their preferred positions, to break bonds, to disrupt the crystalline order. A hard material is one where the atoms resist this disruption, where the bonds are strong, where the structure doesn't easily yield. The rhombohedral structure of boron carbide, with its interconnected icosahedral clusters and linking chains, creates a three-dimensional network where forces applied at any point are distributed throughout the structure. It's like a molecular geodesic dome. Forces can't simply push through. They're redirected, shared among many bonds, resisted by the collective strength of the entire structure. And because boron and carbon are both light elements, near the beginning of the periodic table, with relatively few protons and neutrons in their nuclei, the material achieves this strength without the mass that would come from using heavier elements. This is the secret to that unusual hardness-to-weight ratio we've discussed. The strength comes from the structure, from the arrangement, from the geometry of the atomic architecture, not from sheer atomic mass. But here's something crucial to understand. Boron carbide as a material is not a single perfect crystal. When we manufacture boron carbide components, we're not creating one enormous crystal lattice. Instead, we're creating what's called a polycrystalline material, millions or billions of tiny crystal grains, each with its rhombohedral structure, all pressed together to form the bulk material. And the characteristics of these grains, their size, their distribution, their boundaries, matter enormously to how the material performs. Armor-grade boron carbide uses tightly controlled grain sizes. Imagine looking at boron carbide under a powerful microscope, powerful enough to see its grain structure. You would see a landscape of irregular polygons fitted together like a complex jigsaw puzzle, each piece representing a single crystal grain. Where the grains meet, at the grain boundaries, the perfect crystalline order is interrupted. Atoms at the boundaries are not in their ideal positions. There are gaps, mismatches, discontinuities. These grain boundaries are important. They're weak points, yes, but they're also necessary. A material made of large grains behaves differently from one made of small grains. And for armor applications, grain size becomes a critical parameter that must be carefully controlled during manufacturing. Why? Because grain size affects how cracks form and travel through the material. Fine grains maximize hardness and reduce crack initiation. Let's think about what happens when an extreme force is applied to boron carbide. Say, the impact of a high-velocity projectile. Enormous stresses concentrate at the impact point. The material must either absorb these stresses or fail. In a polycrystalline material, cracks typically don't travel straight through crystal grains. Instead, they prefer to travel along grain boundaries, where the structure is already somewhat disrupted, where the resistance to crack propagation is lower. If the grains are large, a crack that initiates can travel a long distance along a grain boundary, gathering momentum, growing, potentially leading to catastrophic failure. But if the grains are fine, small, then any crack must change direction frequently as it encounters new grain boundaries oriented in different directions. Each time the crack must change direction, energy is absorbed. The crack slows, or branches, or stops entirely. Fine grains also mean more grain boundaries per unit volume, which means more interfaces where the crack must make decisions about which direction to travel. This tortuous path absorbs energy, blunting the crack's ability to propagate rapidly. Additionally, fine grains mean that at any given point on the material's surface, you're likely very close to a grain boundary. This uniformity of structure at small scales contributes to more consistent mechanical properties throughout the material. Fewer weak spots, fewer locations where a crack might find it easy to initiate. But achieving fine grains is not simply a matter of wishing for them. Grain size is controlled during the manufacturing process. Through the initial powder characteristics, through the temperatures used during sintering, through the time allowed at elevated temperatures, through pressure application. And there's a delicate balance to maintain, because grain size can change if conditions aren't carefully controlled. Excessive grain growth weakens impact resistance. During the manufacturing process, when boron carbide powder is heated to consolidate it into a dense solid, the grains want to grow. At elevated temperatures, atoms become more mobile. Grain boundaries can migrate. Small grains can be absorbed by larger neighbors. This is called grain growth, and it's a natural thermodynamic process. Systems tend toward configurations that minimize interface energy, and having fewer, larger grains achieves this. But for armor applications, grain growth is the enemy. If the manufacturing process allows too much grain growth, if the temperature is too high or held for too long, or if the initial powder wasn't properly prepared, the resulting material will have large grains. And as we've discussed, large grains mean longer, easier crack paths, reduced energy absorption, compromised impact resistance. A piece of boron carbide with excessive grain growth might still be hard. It might still measure well on a Vickers hardness test. But when that high-velocity projectile strikes, when the material faces the ultimate test of ballistic impact, it won't perform as well. It will fail more easily. It will not protect as effectively. This is why armor-grade boron carbide requires such tight process control. This is why manufacturers must carefully monitor and control every step of production. The difference between excellent armor and mediocre armor might come down to holding a temperature for 45 minutes versus 60 minutes. or to reaching 2,150 degrees Celsius versus 2,250 degrees. But grain size is not the only microstructural feature that must be controlled. There is another characteristic, another potential flaw that must be minimized. Residual porosity is minimized because pores act as stress concentrators. Porosity means voids, empty spaces within the material where there should be solid boron carbide. Imagine the material as a sponge, but at the microscopic scale. Where there's a pore, there's nothing, just empty space, maybe containing air or vacuum. These pores are problematic for several reasons, but the most critical is that they act as stress concentrators. When a load is applied to a material, the stress, the force per unit area, must be carried by the solid portions. If the material is 100% dense, with no pores, the stress distributes relatively evenly. But if there are pores, the stress must route around them. The solid material between pores must carry more than its proportional share of the load. Think of it like traffic on roads. If all roads are open and functioning, traffic distributes smoothly. But if some roads are closed, if there are gaps, then the remaining roads become congested, stressed beyond their normal capacity. At the microscopic level, pores create regions where stress concentrates intensely at the edges of the void. These stress concentrations can easily exceed the local strength of the material, leading to crack initiation. A crack that starts at a pore then propagates outward, potentially linking with other pores, creating a cascade of failure. For armor applications, this is catastrophic. The projectile impact already creates extreme stress. Adding internal stress concentrators from porosity essentially creates pre-existing weak points, places where failure is more likely to begin. This is why high-performance boron carbide must be nearly fully dense, typically 98% or higher relative to the theoretical maximum density. That remaining 2% or less of porosity must be distributed as tiny, isolated pores rather than connected networks. Every manufacturing technique, hot pressing, hot isostatic pressing, spark plasma sintering, aims to eliminate porosity as completely as possible. But even with controlled grain size and minimized porosity, there's another dimension of control that's absolutely critical to achieving proper material properties. Stoichiometry, the boron to carbon ratio, is carefully controlled. Stoichiometry is a term from chemistry that refers to the quantitative relationships between elements in a compound. For boron carbide with the formula B4C, the stoichiometric ratio is 4 boron atoms to 1 carbon atom. But here's the thing, boron carbide can actually exist across a range of compositions. The formula B4C is somewhat idealized. In reality, boron carbide can have compositions ranging from roughly B4C to B.5C, or even slightly beyond. The exact ratio of boron to carbon can vary, and this variation has profound effects on the material's properties. For armor applications, the stoichiometry must be carefully controlled within a narrow window. Too far in either direction, too much carbon or too little, and problems arise. Too much carbon leaves free graphite. If the manufacturing process includes more carbon than the boron carbide structure can incorporate, if we push past the solubility limit, the excess carbon must go somewhere. And where it goes is into a separate phase, graphite. Graphite is the soft, slippery form of carbon you find in pencils. It's made of carbon atoms arranged in flat sheets that slide easily past each other. And it is absolutely not what you want in your armor material. Free graphite within boron carbide acts as a weakness, a soft inclusion within the hard matrix. When stress is applied, the graphite regions can't carry their share. They act almost like pores, stress concentrators where cracks can easily initiate. The graphite layers can separate, creating internal voids, providing easy paths for crack propagation. A piece of boron carbide with free graphite might look acceptable on the surface. The graphite inclusions might be too small to see with the naked eye. But under impact, the material will underperform dramatically. Ballistic tests that should result in projectile defeat instead result in armor failure, all because of excess carbon creating these weak graphite inclusions. But the opposite error, too little carbon, creates its own set of problems. Too little carbon leaves boron oxide behind. If there's not enough carbon in the initial mixture, or if carbon is lost during processing, perhaps through oxidation if the manufacturing atmosphere isn't perfectly controlled, then we have excess boron relative to what the boron carbide structure can accommodate. This excess boron, especially at the high temperatures used in manufacturing, tends to react with any available oxygen to form boron oxide, B2O3. And boron oxide, unlike boron carbide, is relatively soft. It has a low melting point. It's hygroscopic, meaning it absorbs water from the atmosphere. None of these are characteristics you want in armor material. Boron oxide inclusions within the boron carbide matrix act as weak points, just like graphite does. They're regions that can't carry stress effectively, that create stress concentrations, that provide crack initiation sites and easy crack propagation paths. Worse, if boron oxide is present at grain boundaries, and it often migrates there during manufacturing, it can actively weaken the grain boundaries themselves, making it even easier for cracks to propagate through the material. Can you see the challenge? The manufacturer must walk a tightrope. Too much carbon, free graphite. Too little carbon, boron oxide. The window for optimal composition is narrow, and every batch of raw materials, every manufacturing run, must be carefully controlled to hit that target. This is not a casual process. This is not something that can be done inconsistently and still produce reliable armor. This requires analytical chemistry to verify raw material compositions, careful weighing and mixing, controlled atmospheres during processing, and post-manufacturing analysis to verify that the final product meets specifications. And the consequences of getting it wrong are severe. Either flaw degrades ballistic performance. We've discussed how free graphite creates weak inclusions. We've discussed how boron oxide creates soft phases and weakens grain boundaries. But let's be explicit about what this means when a projectile strikes the armor. Armor works through a complex interaction between the projectile and the armor material. In the case of ceramic armor, like boron carbide, one of the key mechanisms is that the ceramic's extreme hardness actually damages and defeats the projectile. The projectile begins to fracture and erode on impact. But this only works if the ceramic maintains its integrity long enough to accomplish this defeat. If the ceramic has weak inclusions, whether graphite or boron oxide, the stress of impact can cause the ceramic to fail prematurely. Instead of the projectile being defeated, the ceramic fragments catastrophically. The projectile, though damaged, continues through the fragmented ceramic and potentially through any backing material behind it. In a laboratory ballistic test, this appears as a perforation. The projectile punches completely through the armor system. In actual use, protecting an actual person, this means the armor has failed in its fundamental purpose. The weakness created by poor stoichiometry control, invisible to the naked eye, has created a fatal flaw. This is why armor-grade boron carbide is so much more expensive and carefully controlled than industrial-grade boron carbide used for other applications. When you're using boron carbide as an abrasive, or in nuclear applications, or for other purposes, a small amount of free graphite or boron oxide might be tolerable. The material will still function adequately for its intended purpose. But for armor, there is no tolerance for these flaws. The material must be as close to perfect as human manufacturing can achieve. The grain size must be controlled. The porosity must be minimized. The stoichiometry must be precisely maintained. Every piece of armor-grade boron carbide represents a triumph of manufacturing precision, of quality control, of understanding materials at the most fundamental level and controlling them with exquisite care. When you look at that dark, matte surface of a boron carbide armor plate, you're looking at the result of incredible sophistication. You're looking at a material where every cubic millimeter contains billions of properly oriented crystal grains, each with the correct composition, bonded tightly together with minimal porosity, ready to perform its protective function. This is engineering at its finest, not the engineering of massive structures or powerful machines, but the engineering of materials at the microscopic level, where structure determines function, where precision matters more than size, where invisible details make the difference between success and failure. Inside the crystal, inside those rhombohedral structures, inside those carefully controlled grains, inside that precisely maintained stoichiometry, lies the true secret of boron carbide's performance. The dark surface reveals nothing of this internal perfection, nothing of the atomic scale architecture that makes protection possible. But it's there, in every grain, in every bond between atoms, in every carefully eliminated pore, and every precisely controlled composition. The structure is there, waiting, ready for the moment when it will be tested, when a projectile will strike and the material will prove whether all that careful control, all that manufacturing precision, all that understanding of crystalline structure has achieved its purpose. This is boron carbide at its most fundamental level. Not just a material, but a carefully orchestrated arrangement of atoms, engineered for a purpose, controlled with precision, existing as testament to what can be achieved when we understand materials from the inside out. Every material has an origin story, a moment of discovery, a first creation, a journey from concept to reality. For boron carbide, that story begins not in the modern era of advanced materials science, but in the closing years of the 19th century, in a time when chemistry was still revealing the fundamental building blocks of matter. The year was 1894. The place was France, and the man was Henri Moissart, a chemist whose name would become synonymous with innovation and discovery. Boron carbide was first synthesized in 1894 by Henri Moissart. Henri Moissart was no ordinary chemist. He was a pioneer, working at the frontiers of what was possible with the technology and knowledge of his era. He had already made his mark by isolating fluorine, one of the most reactive and dangerous elements, a feat that had defeated many chemists before him and would eventually earn him the Nobel Prize in Chemistry in 1906. But Moissart was also fascinated by high temperatures, by what could be achieved when materials were subjected to extremes of heat that had never before been accessible. He developed the electric arc furnace, a device that could reach temperatures previously unattainable in laboratory settings. With this furnace, he could melt materials that had never been melted, create reactions that had never been observed, synthesize compounds that had never existed. It was in this electric arc furnace, working with boron oxide and carbon, that Moissart first created boron carbide. He heated these materials together to temperatures exceeding 3,000 degrees Celsius, a temperature at which most materials would vaporize or decompose. And when the furnace cooled, he found something new. A black, extremely hard substance that could scratch nearly everything else, that resisted acids, that possessed properties unlike anything else in his laboratory. He had created boron carbide, though he might not have fully understood, at the time, just how significant this material would become. In 1894, there were no armored vehicles to protect, no body armor to manufacture, no industrial applications demanding ultra-hard materials. Boron carbide was a curiosity, a scientific achievement, proof of what could be done with extreme temperatures and the right combination of elements. But curiosities have a way of becoming useful, given time. Commercial production began in the 1930s. Nearly 40 years passed between Moissart's discovery and the first commercial production of boron carbide. 40 years during which the world changed dramatically. The First World War had demonstrated the power and terror of modern weapons. Industry had grown more sophisticated. Materials science had advanced. And the need for hard, wear-resistant materials had become apparent. In the 1930s, companies began developing processes to manufacture boron carbide, not in laboratory quantities measured in grams, but in industrial quantities measured in kilograms and eventually tons. These early commercial producers were primarily interested in boron carbide as an abrasive, a material for grinding and polishing, rather than for armor. But the foundation was being laid for the material's eventual evolution into a protective material. The challenge these early manufacturers faced was significant. How do you take a laboratory curiosity and scale it up? How do you create a process that's reliable, reproducible, economical enough to make commercial sense? The answer they arrived at, the process that still dominates boron carbide production today, is elegant in its concept, though demanding in its execution. Most boron carbide is made by carbothermal reduction. Carbothermal reduction is a term from chemistry, but let's break it down into understandable pieces. Thermal refers to heat, specifically high heat. Reduction refers to a chemical reaction where oxygen is removed from a compound. And carbo- indicates that carbon is the agent doing the reducing, the material that strips away the oxygen. So carbothermal reduction is a process where carbon, at high temperatures, removes oxygen from an oxide compound. It's a transformation, an atomic rearrangement, where oxygen that's bound to other elements is pulled away by carbon's strong affinity for oxygen at elevated temperatures. For boron carbide production, the process works like this. Boron oxide reacts with carbon at extreme temperatures. Imagine a furnace, its interior glowing with heat so intense that the walls themselves are near their melting point. Inside this furnace, we've placed a mixture, boron oxide, a white powder, mixed with carbon, black as coal. At room temperature, these materials could sit together indefinitely without reaction. But as the temperature rises, as the furnace approaches temperatures measured in thousands of degrees, the atomic world becomes active. The boron oxide, B2O3, contains boron atoms bonded to oxygen atoms. The carbon wants to bond with that oxygen. At extreme temperatures, the thermal energy is sufficient to overcome the activation barriers, to break the existing bonds and form new ones. Carbon atoms collide with boron oxide molecules. Bonds break and reform. The oxygen that was bound to boron migrates to carbon instead. Boron atoms, freed from oxygen, bond with carbon and with each other, forming the complex rhombohedral structure we discussed earlier, the crystal lattice of boron carbide. But what happens to the oxygen? It doesn't simply vanish. Elements are conserved in chemical reactions. The oxygen that leaves the boron must go somewhere. This reaction releases carbon monoxide gas. The oxygen, bonded now to carbon, forms carbon monoxide, CO. This is a gas, and at the extreme temperatures inside the furnace, it expands and escapes, bubbling up through the reacting mass, carrying away heat, carrying away the oxygen that would otherwise contaminate the final product. This is crucial. If the oxygen remained in the system, it would form boron oxide inclusions in the final product. Exactly the flaw we discussed in the previous segment. The fact that carbon monoxide is a gas, that it leaves the system, means the oxygen is removed, leaving behind relatively pure boron carbide. But this reaction doesn't happen in just any container, in just any heating device. The temperatures and conditions required are extreme, demanding specialized equipment. Electric arc or resistance furnaces are used. An electric arc furnace works by creating an electrical arc, essentially a sustained lightning bolt between electrodes. The electrical energy converts to heat with extraordinary intensity. Temperatures at the arc itself can exceed 3,000 degrees Celsius. This is the technology that Moissan pioneered, now scaled up to industrial proportions. A resistance furnace works differently, but achieves similar results. Electrical current passes through resistive heating elements, which convert electrical energy to heat. By using materials that can withstand extreme temperatures, and by carefully controlling the electrical input, resistance furnaces can maintain the sustained high temperatures necessary for boron carbide production. Either way, the goal is the same: to achieve and maintain temperatures that most materials cannot survive, to create an environment where the carbothermal reduction reaction can proceed to completion. And just how hot must these furnaces get? Temperatures exceed 2,000 to 2,400 degrees Celsius. 2,000 degrees Celsius. Let's pause and appreciate that number. This is well above the melting point of iron, which sits around 1,538 degrees. This is above the melting point of titanium, of platinum, of most elements and compounds. At these temperatures, the interior of the furnace glows with an intensity that would be painful to look at even through protective glasses. Different manufacturers might optimize their processes for slightly different temperature ranges within this window. Some might run hotter at 2400 degrees or even higher to accelerate the reaction to ensure complete conversion. Others might run slightly cooler at 2000 to 2200 degrees, perhaps to reduce energy costs or to better control grain growth in the final product. But regardless of the specific temperature chosen, the requirement remains: extreme heat, sustained for hours, controlled with precision. And here lies one of the fundamental challenges of boron carbide production. The process is extremely energy intensive. Reaching temperatures of 2000 to 2400 degrees Celsius requires enormous amounts of electrical energy. The furnaces must heat not just the reactants, but also their own containment structures, the surrounding insulation, everything in the thermal system. And they must maintain these temperatures not for minutes, but for hours, allowing the reaction to proceed to completion throughout the entire charge of material. Consider the economics of this. Electrical energy costs money. The more energy required, the more expensive the product becomes. Boron carbide production is fundamentally limited by energy costs. The material's price reflects, in part, the enormous electrical bill required to create it. This is why boron carbide is not a commodity material, not something produced casually or cheaply. Every kilogram of boron carbide represents a significant investment in energy, in equipment operation, in time. But the energy investment is necessary. There are no shortcuts to creating this material. You cannot produce boron carbide at lower temperatures. You cannot speed up the process without risking incomplete reaction or product contamination. The physics and chemistry demand these extreme conditions. And when the reaction is finally complete, when the furnace has been held at temperature for the required time, and the chemical transformation is finished, what emerges? The product emerges as hard fused masses. Inside the furnace, the boron carbide doesn't form as a fine powder. Instead, the reaction products fuse together, melt together, bond together, creating solid masses, chunks of material that might weigh several kilograms each. These masses are incredibly hard, dense, and solid, essentially synthetic rocks of boron carbide. When the furnace is finally allowed to cool, a process that must be carefully controlled to avoid thermal shock that could crack the furnace lining. And when it's opened, workers remove these fused masses. They might be irregular in shape, lumpy, with surfaces that bear the imprint of the crucible or container in which they formed. These masses are the raw product of the carbothermal reduction process. They are boron carbide, but they are not yet in a usable form. An armor manufacturer cannot take a kilogram chunk of fused boron carbide and use it directly. The material must be transformed into a form that can be shaped, consolidated, and formed into armor components. This requires another step, another process, another application of energy and equipment. These must be crushed into fine powder. Crushing boron carbide is not a trivial task. Remember, this is one of the hardest materials on Earth. It's not something you can break apart with a hammer. It's not something that yields to ordinary crushing equipment. Instead, the fused masses must be fed into specialized crushing and milling equipment. Impact crushers, jaw crushers, ball mills lined with boron carbide, or other extremely hard materials. The fused chunks are repeatedly fractured, ground, pulverized into progressively finer particles. This crushing process itself is energy-intensive and time-consuming. The hardness that makes boron carbide valuable as armor also makes it difficult to process. The mills must run for hours, or even days, to reduce the material to the desired particle size. The crushing media, the balls and ball mills, the surfaces in impact crushers, were over time contaminating the product and requiring regular replacement. And particle size matters enormously. Too coarse, and the powder won't consolidate properly during later processing steps. Too fine, and the powder might be difficult to handle, might aggregate, might not flow properly. Armor-grade applications typically require powders with average particle sizes in the range of a few micrometers, small enough to pack densely, large enough to handle reliably. Once crushed into fine powder, the material is typically classified, sorted by particle size using sieves or air classification to ensure uniformity. The powder might be analyzed for purity, for composition, for particle size distribution. Only powder that meets strict specifications proceeds to the next stage of processing. But let's step back for a moment and consider the entire journey we've just traced. From raw materials, boron oxide and carbon, through extreme heat in specialized furnaces, through chemical transformation releasing gases and consuming enormous energy, through cooling and crushing and classification, we arrive finally at a fine black powder. This powder is the starting point for armor production, but it is also the end point of a complex, demanding manufacturing process that traces its roots back to Henri Moissan's laboratory in 1894. Think about the progression of knowledge and capability that this represents. Moissan, working alone in his laboratory, could create perhaps a few grams of material, enough to study, to analyze, to recognize as something new and remarkable. By the 1930s, commercial producers could make kilograms, enough to supply abrasive manufacturers, enough to begin finding industrial applications. Today, modern manufacturers produce tons, enough to supply armor manufacturers worldwide, enough to protect thousands of soldiers and civilians. This scaling up, from laboratory curiosity to industrial commodity, required not just improvements in furnace design or crushing equipment, but fundamental advances in understanding. Understanding of the chemistry, of optimal processing conditions, of how to control composition and purity, of how to achieve consistent results batch after batch. And still, even with all this accumulated knowledge, boron carbide production remains challenging. It remains energy intensive. It remains expensive. It remains a process that demands careful control and specialized expertise. But from these demanding processes, from these extreme temperatures and crushing operations, emerges the raw material that will eventually become armor. The fine black powder, carefully produced and controlled, ready for the next stage of transformation. Consolidation into dense, strong components that will fulfill the promise of protection that lies inherent in boron carbide's remarkable properties. This is how boron carbide is born. Not gently, not easily, but through fire and force, through chemical transformation at temperatures that challenge our equipment and our understanding. From these extreme processes comes a material that will later face extreme conditions in service, protecting human lives through the same hardness and strength that makes it so difficult to produce in the first place. The journey from raw elements to protective armor is long, and it begins here, in the crucibles and furnaces where carbon strips oxygen from boron, where new bonds form and gases escape, where something new and extraordinary emerges from the heat and light of industrial synthesis. We have traced boron carbide from its discovery, through its commercial production, to the fine black powder that emerges from crushing and classification. But powder by itself is not armor. Powder cannot stop a bullet. Powder cannot protect a soldier or shield a vehicle. The transformation from powder to protective component requires another series of steps, another application of specialized knowledge and equipment. This is where manufacturing becomes something almost like magic, where loose particles are transformed into dense, solid structures, where careful control of temperature and pressure creates materials with properties that seem to defy common sense. Let us follow this transformation, step by step, from raw materials to finished armor components. But first, we should understand where this journey truly begins. Not with pure elements, but with practical, available raw materials. Raw materials include boric acid and petroleum coke. When we discussed carbothermal reduction, we spoke of boron oxide and carbon reacting at high temperatures. But in industrial practice, manufacturers often start with materials that are more readily available, more economical, or more convenient to handle. Boric acid, H3BO3, is a common starting material for boron sources. It's a white crystalline solid, relatively safe to handle, readily available from mineral deposits or chemical suppliers. When heated, boric acid dehydrates, losing its water molecules and transforming into boron oxide. The B2O3 that participates in the carbothermal reduction reaction. Petroleum coke, often called pet coke, serves as the carbon source. This is a byproduct of oil refining, a solid carbon-rich material that results from processing heavy petroleum fractions. It's less pure than graphite, but it's considerably less expensive, and for carbothermal reduction purposes, it provides the carbon needed for the reaction. So the process begins with these practical materials, boric acid and petroleum coke, measured in precise ratios, mixed together, ready to be transformed in the furnace. But even after the furnace has done its work, even after crushing and classification, the production process is not purely linear. There's an aspect of efficiency, of resource management, that practical manufacturers employ. Furnace returns are often recycled to improve efficiency. During the carbothermal reduction process, not everything converts perfectly. There might be unreacted materials. There might be partially converted masses. When the fused material is crushed, some of it might not meet specifications. Perhaps the composition is slightly off, or there are inclusions that make it unsuitable for high-grade applications. Rather than discarding these materials, manufacturers often recycle them back into the process. These returns can be reground and added to fresh batches of raw materials going into the furnace. The unreacted boron oxide, or carbon, gets another chance to participate in the reaction. The slightly off-spec material gets diluted by fresh, properly formulated batches. This recycling improves material efficiency. Less waste means lower raw material costs. It also improves energy efficiency somewhat, as the returns have already been partially processed and might require less energy to complete the transformation. But whether from virgin raw materials or from recycled returns, the resulting powder, that fine black boron carbide powder we ended the last segment with, still requires further processing before it can become armor. Powders are ground, purified, and magnetically separated. Even after the initial crushing and classification, the powder may not be perfect. Particle size distribution might need refinement, perhaps finer grinding to break up remaining agglomerates, to achieve a more uniform particle size that will pack more densely during consolidation. Purification might involve chemical treatments, washing with acids or other solutions to dissolve impurities, followed by rinsing and drying. The goal is to remove anything that isn't boron carbide, anything that would compromise the final material's properties. And then there's magnetic separation, a surprisingly important step for such a non-metallic material. Why magnetic separation? Because during processing, during crushing in mills lined with hard materials, during grinding, during handling in equipment, small amounts of metallic contamination can be introduced. Tiny particles of iron or steel from equipment wear, fragments from crushing media, metallic dust from the processing environment. Magnetic separators use strong magnetic fields to pull these metallic particles out of the powder stream. The boron carbide, being non-magnetic, passes through. The iron and steel particles are captured and removed. This might seem like a small detail, but remember what we discussed about impurities and their effects on ballistic performance. Impurities like iron or silica must be removed. Iron particles in boron carbide armor would create soft inclusions, stress concentrators, weak points. When a projectile strikes, the stress would concentrate around these iron particles. Cracks could initiate at the iron inclusions and propagate outward. The armor would fail prematurely, its performance degraded by contamination measured, perhaps in parts per thousand, or even parts per million. Silica, silicon dioxide, essentially fine sand, could come from impure raw materials or from contamination during processing. Like iron, silica creates inclusions that don't belong, that disrupt the uniform boron carbide matrix, that compromise mechanical properties. For armor-grade boron carbide, total impurity levels must be kept extremely low, typically well below 1% and preferably much lower. Every purification step, every magnetic separation pass, every careful handling procedure contributes to achieving this purity. Only when the powder meets these strict purity requirements, only when it has the right particle size distribution and composition, can it proceed to the next stage, consolidation. And consolidation begins with a process that might seem almost mundane compared to the extreme temperatures we've been discussing. Powder is pressed into green bodies. The term green in ceramics doesn't refer to color. It refers to a state, unfired, unconsolidated, held together only by pressure and perhaps a small amount of temporary binder, not yet transformed by heat into its final dense form. The process works like this. Boron carbide powder is loaded into a die, essentially a mold, with precisely shaped cavity. A punch or ram then presses down on the powder with controlled force, measured in tons. The powder compacts, particles sliding past each other, filling voids, packing more tightly. Sometimes a small amount of organic binder is added to the powder first, perhaps a few % by weight of a polymer that will later burn away during heating. This binder helps the pressed shape maintain its form when it's removed from the die, prevents crumbling, makes the green body easier to handle. The press might be hydraulic or mechanical, capable of applying pressures from several tons to hundreds of tons, depending on the size of the part being formed. The pressure is applied uniformly, or as uniformly as possible, to create a compact that has consistent density throughout. But even with significant pressing force, the resulting green body is still far from fully dense. These reach about 60% theoretical density before sintering. Think about what 60% density means. If the material were fully dense, if there were no voids, no gaps between particles, it would be 100% of theoretical density. At 60%, that means 40% of the volume is empty space, voids between particles, air trapped in the pressed powder compact. You could hold this green body in your hand. It would feel solid, would maintain its shape, but it would be relatively fragile. You could break it with your hands if you tried. It certainly couldn't stop a bullet. Those voids, that 40% empty space, would make the material far too weak for armor applications. The green body is really just a starting point, a convenient form that can be handled, moved, loaded into furnaces for the critical next step, sintering. Sintering is the process where the real magic happens, where loose powder transforms into dense, strong ceramic. Pressureless sintering occurs at 2,300 to 2,400 degrees Celsius. Pressureless means exactly what it sounds like, sintering that occurs at high temperature, but without external pressure being applied. The green bodies are placed in a furnace, often in a protective atmosphere, or even in vacuum to prevent oxidation, and the temperature is raised to 2,300 to 2,400 degrees Celsius. At these extreme temperatures, remember, these are temperatures where most materials melt or decompose. Something remarkable happens at the atomic level. The boron carbide particles begin to bond to each other. Atoms diffuse across particle boundaries. The surface energy drives the system toward a lower energy state, which means fewer interfaces, more solid contact between particles. Gradually, over hours at these temperatures, the particles fuse together. Necks form between adjacent particles. These necks grow, thickening, creating solid bridges of material where before there were only point contacts or small voids. The voids themselves migrate and consolidate, many small voids becoming fewer larger voids, and those voids gradually shrinking, closing, being filled by material diffusion. The part shrinks during this process. That 60% dense green body might shrink by 15 or 20% in its linear dimensions as it consolidates to perhaps 92 to 95% density. The shapes must be designed with this shrinkage in mind. Parts are made oversized in the green state, so they'll be the correct size after sintering. But pressureless sintering, while effective, has limitations. Achieving very high densities, above 95 or 96%, becomes progressively more difficult. The remaining porosity becomes trapped, and without external driving force, it's hard to eliminate completely. This is where pressure-assisted sintering becomes valuable. Hot pressing applies pressure during heating. Hot pressing combines temperature and pressure simultaneously. The green body is placed in a die that can withstand extreme temperatures, perhaps made of graphite, which can survive these conditions. The entire assembly is heated while pressure is applied through rams that push on the powder compact from one or both directions. The combination is powerful. The high temperature promotes atomic diffusion and particle bonding, just as in pressureless sintering. But the applied pressure provides additional driving force, physically pushing particles together, helping to collapse voids, forcing the material to densify. Hot pressing can achieve densities of 97 to 99%, significantly higher than pressureless sintering alone. The resulting material is stronger, has fewer defects, has better and more consistent mechanical properties. But hot pressing has some limitations too. The pressure is typically uniaxial, applied from one direction or from opposite directions, which can create slight density gradients in complex shapes. The dies and equipment are expensive and have limited life. Production rates are lower than batch furnace sintering. For the ultimate in density, for applications where maximum performance is essential, there's another technique. HIP can push density beyond 99%. HIP stands for hot isostatic pressing. Isostatic means equal pressure from all directions. Unlike hot pressing where pressure is directional, in HIP the pressure surrounds the part completely and uniformly. HIP works by placing the part, often already sintered to high density through hot pressing or pressureless sintering, into a pressure vessel. The vessel is then heated and pressurized with an inert gas, typically argon, to very high pressures, often exceeding 15,000 pounds per square inch, at temperatures around 2,000 degrees Celsius or higher. The gas pressure acts equally on all surfaces of the part, squeezing from all directions simultaneously. Any remaining porosity, even tiny isolated pores that survived earlier processing, is forced to close. The material consolidates to densities beyond 99%, approaching the theoretical maximum. At these densities, the material's properties reach their peak. Mechanical strength is maximized. Ballistic performance is optimized. The armor performs as close to its theoretical best as manufacturing can achieve. But achieving this performance comes at a cost. HIP equipment is expensive. Operating at these extreme pressures and temperatures requires specialized vessels, careful control, significant energy consumption. HIP adds time to the manufacturing process and adds cost to the final product. For the most demanding armor applications, where performance is paramount and cost is secondary, HIP processing is worthwhile. For less demanding applications, hot pressing or even pressureless sintering might be sufficient. But regardless of which consolidation process is used, the result is the same: a dense, hard, strong piece of boron carbide, transformed from powder into solid ceramic, ready to serve as armor. Almost ready, anyway. There's typically one more step required. Finished tiles are machined with diamond tools. The sintered boron carbide emerges from the furnace with surfaces that might be rough, with dimensions that might not be precisely what's needed, with edges that aren't quite right. For armor applications, dimensions matter. The tiles must fit precisely into armor arrays. Thicknesses must be controlled. Edges must be beveled or chamfered to prevent chipping. But how do you machine a material that's one of the hardest substances on Earth? How do you cut, grind, or drill boron carbide when it's harder than almost every tool material? The answer: you use the few materials that are harder. Specifically, you use diamond. Diamond grinding wheels, with industrial diamonds embedded in a metal matrix, are used to grind boron carbide to final dimensions. Diamond saws, with diamond cutting edges, are used to cut it. Diamond drills are used if holes are needed. The machining process is slow. Diamond tools cutting boron carbide wear relatively quickly. Even diamond, the hardest natural material, wears when grinding another ultra-hard ceramic. The process generates dust that must be carefully controlled and captured. Coolants must be used to manage heat and to flush away grinding debris. Each tile might require hours of machining time to achieve final dimensions within the required tolerances, typically a few hundredths of a millimeter or better. The tiles are measured repeatedly during machining adjusted, remeasured, refined until they meet specifications. And only then, only after this complete journey from raw materials through furnacing, crushing, purification, pressing, sintering, and diamond machining, is the armor tile complete. Think about everything that had to happen to create that finished tile. The raw materials had to be sourced and prepared. The furnace had to reach temperatures exceeding 2000 degrees, consuming vast amounts of electrical energy, transforming boric acid and petroleum coke into boron carbide. The fused material had to be crushed with specialized equipment. The powder had to be purified, magnetically separated, carefully controlled for particle size and composition. The powder had to be pressed into shape, carefully loaded into dies, compacted under controlled pressure. The green body had to be sintered at temperatures approaching 2,400 degrees Celsius for hours, or hot pressed with simultaneous temperature and pressure, or even hit processed with extreme pressures from all directions. And finally, the hard-won dense ceramic had to be machined with diamond tools, ground and cut to final dimensions, finished to specifications. Every step required specialized knowledge. Every step required expensive equipment. Every step required careful control and verification. Every step added cost, added time, added complexity to the manufacturing process. And yet, despite all this effort, despite all this expense and complexity, manufacturers around the world undertake this process because the result, that finished boron carbide armor tile, provides protection that justifies the investment. This is the transformation from powder to armor. This is the manufacturing magic that takes loose particles and creates dense, hard, protective components. It's not actually magic, of course. It's materials science, it's engineering, it's the careful application of known physical and chemical principles. But the results can seem almost magical. A dark ceramic tile, weighing just a fraction of what steel armor of equivalent protection would weigh, capable of stopping projectiles that would defeat other materials, ready to protect human lives. From boric acid and petroleum coke to finished armor. The journey is long, demanding, and expensive, but the destination makes it worthwhile. The finished tiles, emerging from diamond machining with precisely controlled dimensions and surfaces, represent the culmination of more than a century of materials science, from Moissot's first synthesis to modern production techniques that push the boundaries of what manufacturing can achieve. This is how boron carbide powder becomes armor. This is the process, the sequence, the manufacturing pathway that transforms potential into protection, that makes the remarkable properties of boron carbide available for practical use in defending against ballistic threats. We have followed boron carbide from discovery to synthesis, from powder to finished armor tile. We have explored its structure, its properties, its manufacturing. But now we must address the fundamental question, the reason this material exists in armor applications at all. How does it actually work? When a bullet strikes boron carbide armor, traveling at speeds that can exceed 3 times the speed of sound, carrying kinetic energy sufficient to punch through steel plate, what happens in that critical fraction of a second? How does this dark ceramic, so carefully manufactured, so precisely controlled, fulfill its purpose of protection? The answer involves physics that seems almost counterintuitive, a mechanism that relies not on the ceramic remaining intact, but on its controlled destruction. Let us explore this moment of impact, this violent interaction where protection is achieved through processes measured in microseconds. Boron carbide defeats bullets through rapid comminution. Comminution. It's not a word we use in everyday conversation. It comes from the Latin word meaning to reduce to minute particles. Essentially, the process of breaking something into very fine pieces, of pulverizing it, of shattering it into fragments so small they approach powder. And this is exactly what happens when a high-velocity projectile strikes boron carbide armor. The ceramic doesn't simply crack or fracture into a few large pieces, the way a dropped plate might. Instead, it undergoes extremely rapid comminution, breaking into countless tiny fragments in the immediate vicinity of the impact point. Think about what this means. In less than the blink of an eye, in microseconds, the organized crystal structure we discussed, those carefully controlled grains, that rhombohedral lattice, those boron and carbon atoms bonded in their specific arrangement, all of that structure is violently disrupted. The ceramic, locally, ceases to be a coherent solid and becomes something more like a dense cloud of hard particles. This might sound like failure. After all, we've spent so much time discussing the strength of boron carbide, its hardness, its carefully controlled properties. Why would we want it to shatter? The answer becomes clear when we understand what happens next. The ceramic shatters into fine powder under impact. The shattering is not random. It's not uncontrolled failure. It's a specific response to the extreme stress state created by hypervelocity impact. When a projectile traveling at 800, 900, or even 1,000 meters per second strikes a ceramic surface, it creates stress levels that vastly exceed even the remarkable strength of boron carbide. No material, no matter how strong, can remain intact under such conditions. The question is not whether the material will fail, but how it will fail, and whether that failure mode can be exploited for protection. Boron carbide's brittle nature, normally considered a disadvantage in structural applications, becomes an advantage here. The material fractures into fine fragments rather than deforming plastically. And the hardness of those fragments, remember, boron carbide remains one of the hardest materials even when fractured, becomes crucial to what happens next. The impact creates a region of comminuted ceramic directly under the projectile. This region is typically cone-shaped, with the point of the cone at the impact site and the base extending back into the ceramic. Within this cone, the ceramic has transitioned from a coherent solid into a collection of fine particles. Powder, still densely packed, still in contact with each other, but no longer held together by the original crystal structure. And this powder, this debris cloud of hard particles, becomes the mechanism of defeat. This creates a debris cloud under the projectile. Imagine, if you will, a high-speed video camera capable of capturing 1,000,000 frames per second, pointed at a boron carbide tile at the moment of bullet impact. If we could watch this video in extreme slow motion, we would see the projectile approaching, striking the surface, and immediately creating a cone of pulverized ceramic that spreads both backward into the tile and laterally along the impact face. This debris cloud is not like dust or smoke. It's dense, thousands of hard particles in close contact, pressed together by the enormous forces of impact. It's confined, trapped between the projectile and the intact ceramic behind it, unable to easily escape laterally. It's dynamic, constantly being fed new particles as the fracture cone propagates, constantly being compressed and pushed by the advancing projectile. The projectile, instead of encountering solid ceramic along its entire penetration path, now encounters this debris cloud. And this changes everything about the physics of penetration. When a penetrator tries to push through solid material, the material must either be compressed, displaced to the sides, or sheared away. Each of these processes requires energy, but for a hard, dense projectile striking softer materials, the energy required might be less than the projectile's kinetic energy, allowing penetration to continue. But when a penetrator encounters a debris cloud of extremely hard particles, particles of boron carbide with hardness values approaching 30 gigapascals, different physics apply. The debris erodes the penetrator tip. Each particle in the debris cloud is extraordinarily hard as the intact ceramic from which it came. When the projectile tries to push through this cloud, its leading surface, the tip that's designed to concentrate stress and penetrate armor, encounters thousands of hard particles in rapid succession. The projectile tip begins to abrade, to wear, to erode. Small fragments are torn from the projectile surface. The carefully shaped tip that was designed to be aerodynamic and penetration efficient begins to mushroom, to deform, to lose its advantageous geometry. If the projectile has a hardened steel core, that core begins to wear against the boron carbide particles. If it's a tungsten carbide penetrator, extremely hard itself, even tungsten carbide will erode when forced through a dense cloud of boron carbide particles at hypervelocity. This erosion is not a slow process like wind wearing away a rock over millennia. This is extremely rapid erosion, occurring in microseconds, but the principle is similar. Hard particles are braiding against a surface, removing material, degrading structural integrity. And as the tip erodes, as the projectile loses its penetration efficiency, its ability to continue boring through the armor decreases. Energy that should be going into penetration is being consumed in eroding the projectile itself, in pushing aside the debris cloud, in generating heat and sound and deformation. But erosion is not the only mechanism at work. There's another effect, equally important. It deflects the bullet laterally. The debris cloud, confined and dense, doesn't simply allow the projectile to pass through unimpeded. The cloud exerts forces on the projectile from all sides. Forces that might not be perfectly symmetrical, might not be perfectly aligned with the projectile's trajectory. These asymmetric forces cause the projectile to yaw, to tilt, to deviate from its straight path. A projectile that was traveling perpendicular to the armor surface might begin to tilt, to angle, to move laterally as well as forward. This lateral deflection is crucial. Once a projectile begins to yaw, it presents a larger cross-section to the armor. A bullet traveling point first presents minimal area, just the tip. But a bullet that's tilted presents its side, its length, a much larger area that must push through the debris cloud. Increased area means increased resistance. More debris particles are contacted per unit of penetration distance. More erosion occurs across a broader surface. Energy is consumed more rapidly. The combination of erosion and deflection creates a synergistic effect. The erosion makes deflection easier because the tip loses its ability to stay aligned, and the deflection makes erosion more effective because more surface area is exposed to the abrasive particles. And through all of this, through the erosion and deflection and interaction between projectile and debris cloud, something critical is happening to the energy of the impact. Energy spreads over a wider area. When the projectile first strikes, all its kinetic energy is concentrated at the point of impact. A very small area, perhaps just a few square millimeters. The stress at this point is astronomical, which is why the ceramic comminates so readily. But as the projectile erodes and deflects, as it creates a wider cone of comminuted ceramic, as it slows and deforms, its energy spreads. The cone of damaged ceramic grows wider. The forces are transmitted over a larger area of the backing structure behind the ceramic. This is mechanically advantageous. Imagine pressing a needle into your palm. The concentrated force at the sharp point can easily penetrate your skin. Now imagine pressing your palm against a flat board with the same total force. No penetration occurs because the force is distributed over a much larger area, making the stress at any single point much lower. The armor system is doing the same thing, taking the concentrated energy of the projectile and spreading it over a larger area, reducing the peak stress, making it more likely that the backing structure can absorb and dissipate the remaining energy without failure. But all of this, the comminution, the debris cloud formation, the erosion, the deflection, the energy spreading, requires something fundamental from the ceramic itself. The ceramic sacrifices itself to stop penetration. This is perhaps the most important concept to understand about ceramic armor. The ceramic does not stop the bullet by remaining intact, by simply being too strong to penetrate. Instead, the ceramic stops the bullet by breaking in a controlled and advantageous way, by transforming from coherent solid into debris cloud, by using its hardness in fragmented form to erode and defeat the threat. The armor tile is single use at the impact point. After defeating a projectile, the ceramic in and around the impact site is destroyed, comminuted into fine powder, fractured into fragments, no longer capable of providing protection at that location. This is why ceramic armor often includes multiple tiles rather than single large plates. If one tile is impacted, the others remain intact. This is why ceramic armor backing is so important. The backing must contain the damage, must prevent the comminution from spreading indefinitely through the armor system. The ceramic sacrifices itself. It gives up its structural integrity, It's carefully manufactured perfection to achieve protection. It's a one-time use of that particular section of material. But that sacrifice accomplishes something remarkable. It stops threats that would easily defeat armor of similar weight made from steel or other materials. And what happens to the energy that remains after the ceramic has done its work? After the projectile has been eroded and deflected? After the kinetic energy has been partially dissipated? Polymer or fiber backings absorb remaining energy. Behind the ceramic tile sits backing material, typically high-strength polymers like Kevlar or ultra-high molecular weight polyethylene, woven into fabrics, laminated into sheets. These materials are flexible, tough, energy-absorbing. When the comminuted ceramic and the eroded, deflected projectile press against this backing, the fibers deform. They stretch. They absorb energy through deformation without breaking. The aramid molecules, or polyethylene chains in the fibers straighten and align, dissipating kinetic energy as heat. The backing also helps contain the ceramic debris, preventing it from being ejected backwards at high velocity, which could itself be a threat. The backing spreads the load, prevents the ceramic fragments from being driven through as discrete projectiles. This is why armor is a system, not just a material. The hard ceramic defeats the primary threat through comminution and erosion. The fiber backing catches what remains, absorbs residual energy, provides structural support. Together, they provide protection that neither could achieve alone. And there's one more crucial aspect to how this system works, one more requirement for optimal performance. The system works best under compressive stress. Ceramics in general, and boron carbide specifically, are much stronger in compression than in tension. If you try to pull a ceramic apart, it will fail at relatively low stresses. But if you try to compress it, to squeeze it, it can withstand enormously high loads. This is why ceramic armor often includes confinement. The tiles are held in frames, bonded to backings, constrained from expanding laterally. This confinement puts the ceramic under slight compressive stress even before impact, and ensures that during impact, the ceramic experiences primarily compressive loads rather than tensile loads. When the projectile strikes, it creates a compressive stress wave that propagates through the ceramic. The material's high compressive strength allows it to initially resist this stress while the comminution process begins. As the debris cloud forms, it's still under compression, still densely packed, still able to exert the abrading forces on the projectile. If the ceramic were in tension during impact, it would fail more easily, would fragment less controllably, would be less effective at maintaining the dense debris cloud necessary for projectile erosion and deflection. The confinement provided by backing materials, by edge frames, by the overall armor system design, ensures the ceramic can work in its preferred stress state, compression, maximizing its effectiveness. And when all these mechanisms work together, the rapid comminution, the debris cloud formation, the hard particle erosion, the lateral deflection, the energy spreading, the sacrificial destruction of the ceramic, the backing absorption, all occurring under advantageous compressive stress, the result is remarkable. It's brutally effective against rifle rounds. Military rifle rounds, the kinds of threats that armor must defeat to be useful in combat, travel at velocities between 800 and 1,000 meters per second. They carry kinetic energies, measured in thousands of joules. They're designed to penetrate, to defeat protection, to reach targets behind barriers. Against these threats, steel armor of practical thickness and weight is often insufficient. A steel plate thick enough to reliably stop modern armor-piercing rifle rounds would weigh so much that soldiers couldn't wear it. Vehicles couldn't carry enough of it. Aircraft would be too heavy to fly efficiently. But boron carbide armor, working through the mechanisms we've described, can defeat these threats at a fraction of the weight. A boron carbide tile, perhaps 6 to 7 millimeters thick, backed by appropriate fiber layers, can stop rifle rounds that would penetrate 12 to 15 millimeters of hardened steel. The effectiveness comes from that combination of extreme hardness creating effective erosion, controlled comminution creating the debris cloud mechanism, and the system design that allows these mechanisms to work optimally. Soldiers survive impacts that would have been fatal with heavier armor they couldn't carry. Vehicles maintain mobility while achieving protection levels that would have required impractical armor weight with conventional materials. The brutal effectiveness of boron carbide armor has saved countless lives in conflicts around the world. The dark ceramic tile, looking so unassuming, proves its worth in that microsecond of impact. The carefully controlled microstructure, the precisely manufactured composition, the grain size and density optimization, all of these factors we've discussed in previous segments, they all contribute to this moment of defeat, when the armor fulfills its purpose. It's a violent process, a destructive process, a process that sacrifices the material itself. But it's also an elegant process, a physical demonstration of how understanding materials at the deepest level, understanding structure and properties and failure mechanisms, allows us to design protection that seems almost impossible. Boron carbide doesn't try to be impenetrable. It doesn't resist with brute force alone. Instead, it breaks intelligently, strategically, creating conditions that turn its hardness and brittleness into advantages, that transform a penetrating threat into eroded debris, that spreads concentrated energy into manageable loads. This is how boron carbide stops bullets. This is the physics of ceramic armor impact, the mechanisms that have made this material indispensable in modern protective systems. From the first instant of contact through the formation of the debris cloud, through erosion and deflection and energy absorption, the armor system, ceramic and backing working together, achieves protection that justifies all the complexity, all the expense, all the manufacturing precision required to create it. We have journeyed through the science of boron carbide, its discovery, its manufacture, its atomic structure, the physics of how it defeats projectiles. We have explored the material in laboratories and furnaces, examined it at the microscopic level, understood the mechanisms that make it effective. But now we must leave the realm of theory and enter the real world, where this remarkable material fulfills its ultimate purpose, saving lives, not in the abstract, not as a concept or a possibility, but concretely, measurably, every single day. On battlefields and in urban operations, in military vehicles and aircraft, in the hands of soldiers and law enforcement officers around the world. This is where boron carbide proves its worth, where all that careful engineering and manufacturing precision translates into human survival. Let us explore how this dark ceramic has become indispensable to those who face danger, who place themselves in harm's way, who need protection that won't fail them when it matters most. And we should begin with perhaps the most compelling advantage that boron carbide offers in practical use. Boron carbide armor can be 30% lighter than steel systems. 30%. Let that number settle in your mind for a moment. Not a marginal improvement, not a slight advantage, but a fundamental transformation in what's possible. Imagine you're carrying 50 pounds of equipment, weapons, ammunition, communications gear, water, medical supplies, and armor. Now imagine reducing that armor weight by 30%. That's several pounds freed up, several pounds of burden removed. Those pounds matter. They matter when you're patrolling for hours in desert heat. They matter when you're climbing stairs in an urban environment. They matter when you need to sprint to cover, when you need to help a wounded comrade, when you need to maintain alertness and combat effectiveness over extended periods. The human body has limits. Endurance has limits. The more weight a soldier carries, the faster fatigue sets in, the slower movements become, the more energy is consumed just moving from place to place. Reducing armor weight while maintaining protection isn't just about comfort. It's about combat effectiveness, about survivability through maintained speed and agility, about being able to execute the mission successfully. And this weight advantage has profound implications for who can use the best protection available. Elite military units favor it for mobility. Special operations forces, airborne units, rapid response teams. These are units where mobility is paramount, where every kilogram is scrutinized, where the ability to move quickly and efficiently can mean the difference between mission success and failure, between life and death. These units operate differently from conventional forces. They might insert by parachute or helicopter into remote areas. They might need to patrol long distances on foot. They might conduct operations that require climbing, swimming, fast roping from helicopters, or other physically demanding activities. For these operators, heavy steel armor is often simply not feasible. The weight penalty is too severe. But going without adequate protection is not acceptable either. These units often face significant threats, and losing personnel is both morally unacceptable and tactically devastating. Boron carbide armor offers a solution to this dilemma. Protection levels that would require impractically heavy steel armor become achievable in weight budgets that elite units can accommodate. Operators can wear comprehensive armor coverage, torso, sides, vital organs fully protected, without being so burdened that they can't perform their missions. This is democratization of protection, making the highest levels of ballistic protection available not just to vehicle crews or static positions, but to dismounted infantry, to special operators, to anyone who needs to move and fight. And the applications extend beyond full torso coverage to more specific armor solutions. It's used in advanced body armor plates. Modern body armor systems typically consist of a soft armor vest, layers of aramid or polyethylene fibers that protect against handgun rounds and fragmentation, with pockets that can accept hard armor plates for protection against rifle threats. These plates, inserted into pouches on the front and back of the vest, are where boron carbide has found perhaps its most widespread military application. A typical rifle-rated armor plate might measure 10 inches by 12 inches, designed to cover the vital organs: heart, lungs, major blood vessels. Plates made from boron carbide ceramic with appropriate backing materials can stop multiple hits from military rifle rounds. 7.62 mm NATO, 5.56 mm, even armor-piercing variants, while weighing 5 to 6 pounds per plate. Equivalent protection from steel would require plates weighing 8 to 10 pounds or more. That 2 to 4 pound difference per plate, multiplied by front and back plates, represents a significant burden reduction. A soldier wearing boron carbide plates instead of steel saves perhaps 4 to 8 pounds of weight while maintaining the same protection level. Over the course of a 12-hour patrol, over multiple days of operations, that weight saving translates to reduced fatigue, maintained alertness, better combat performance. The plates are typically curved to match the contours of the human torso, improving comfort and weight distribution. They're coated or covered to protect against environmental damage and to prevent the hard ceramic edges from causing discomfort. They're designed to be easily inserted and removed from plate carriers, allowing soldiers to adjust their protection level based on the mission threat assessment. And beyond standard torso plates, boron carbide enables protection concepts that would be impossible with heavier materials. Thin plates enable low-profile covert protection. Not all protective missions are military. Law enforcement officers, diplomats, security personnel, journalists in conflict zones. Many people face ballistic threats, but cannot wear obviously visible armor. They need protection that's concealable beneath normal clothing, that doesn't advertise its presence, that allows them to blend into civilian environments while still providing life-saving protection. This is where the thinness achievable with boron carbide becomes crucial. A boron carbide plate designed to defeat handgun threats might be only 4 to 5 mm thick. With appropriate backing and cover materials, the total thickness might be less than a centimeter, thin enough to wear beneath a business suit or casual clothing without obvious bulges or restricted movement. Steel armor of equivalent protection would be perhaps twice as thick, creating visible bulk that defeats the purpose of covert protection. The thinner boron carbide solution allows discreet protection, allowing the wearer to maintain a normal appearance while having protection immediately available if needed. Security professionals protecting high-value individuals, undercover officers working in dangerous environments, diplomats visiting unstable regions, all benefit from this concealable protection that boron carbide makes possible. But individual protection, critical as it is, represents only part of boron carbide's real-world application. Vehicles, too, need armor, and here the weight advantages become even more dramatic. Military vehicles use boron carbide armor kits. Armored vehicles have a fundamental problem. Armor weight degrades every other aspect of vehicle performance. More armor means slower acceleration, reduced top speed, worse fuel economy, greater stress on suspension and drivetrain components, reduced range between refueling. For vehicles designed from the ground up as armored platforms, main battle tanks, infantry fighting vehicles, this is somewhat manageable. The entire vehicle design accounts for armor weight. Engines are sized appropriately, suspensions are reinforced, fuel capacity is increased. But what about vehicles that weren't designed for armor? Light trucks, utility vehicles, commercial vehicles pressed into military service? Adding conventional armor often means the vehicle becomes dangerously overloaded, struggles to perform, experiences accelerated wear and mechanical failures. Boron carbide armor kits offer a solution. Modular armor panels, designed to mount on doors, floors, behind seats, can provide protection against rifle fire and roadside bombs, while adding significantly less weight than steel armor would. A door panel that might weigh 50 pounds in steel could weigh 35 pounds in boron carbide, while providing equivalent or superior protection. Multiply this across all the armor surfaces on a vehicle. Multiple doors, floor panels, roof reinforcement, and the weight savings compound. A vehicle that would have been overloaded with steel armor remains within its designed weight capacity with boron carbide armor, maintaining acceptable performance while gaining life-saving protection. This has been particularly valuable in asymmetric conflicts where light vehicles face threats they weren't designed to resist. Armor kits can be installed relatively quickly, providing immediate protection improvement without requiring completely new vehicles. And the weight advantage becomes even more critical when we consider vehicles where every pound has extreme importance. Aircraft integrated into floors and pilot seats. Flying machines are perhaps the most weight-sensitive vehicles that exist. Every pound of weight in an aircraft requires fuel to lift and carry. Every pound reduces range, reduces payload capacity, affects performance and handling. Yet aircraft, especially military helicopters and transport aircraft, face significant ground fire threats. Small arms fire, rocket-propelled grenades, anti-aircraft fire, all threaten aircraft during takeoff, landing, and low-level operations. Protecting critical areas, cockpits where pilots sit, floor areas that might face fire from below, seats that must protect aircrew from ground fire, requires armor. But the weight constraints are severe. A helicopter that's too heavy can't hover effectively, can't carry its intended payload, might not be able to operate in high altitude or high temperature conditions. Boron carbide armor, with its exceptional protection-to-weight ratio, has become standard in many military aircraft. Pilot seats incorporate boron carbide plates beneath the cushions, protecting from fire coming up through the floor. Cockpit floors include boron carbide tiles to protect against ground fire during approach and departure. Critical systems might have boron carbide shielding. The protection comes with minimal weight penalty, often just tens of pounds added to an aircraft that weighs thousands or tens of thousands of pounds. But those tens of pounds of armor can save the lives of aircrew worth years of training and experience, can keep multi-million-dollar aircraft flying despite hits that would otherwise down them, can mean the difference between mission completion and catastrophic failure. The same weight advantage that helps dismounted soldiers helps aircraft maintain their performance margins while gaining crucial protection. And boron carbide's applications extend beyond military use into law enforcement contexts, where different requirements drive adoption. SWAT teams deploy boron carbide ballistic shields. When law enforcement tactical teams need to approach a barricaded suspect, enter a building with an active shooter, or conduct high-risk operations, they often use ballistic shields, large protective panels that officers can carry in front of them, providing mobile cover during movement. These shields must be large enough to protect the officer's torso and head, perhaps 20 inches wide by 36 inches tall. They must have a viewing port so the officer can see while protected. And critically, they must be light enough that an officer can carry and maneuver the shield effectively, sometimes for extended periods, while also potentially carrying a weapon and other equipment. A shield made from traditional armor materials, providing rifle-level protection at these dimensions, would weigh 40, 50, even 60 pounds or more. Heavy enough to quickly exhaust even a strong officer, heavy enough to slow movement to a crawl, heavy enough to compromise the tactical flexibility that SWAT teams need. Boron carbide ballistic shields, with their ceramic construction and polymer backing, can provide equivalent protection at perhaps 25 to 35 pounds. Still heavy, still demanding, but manageable for trained officers. Light enough to allow relatively agile movement. Light enough to hold for extended periods if necessary. These shields have saved officers' lives in active shooter situations, in hostage rescues, in high-risk warrant service. The officer behind the shield, advancing toward danger to protect civilians or apprehend threats, relies on that ceramic barrier to turn aside bullets that would otherwise be fatal. And the engineering of these armor systems, whether for individuals, vehicles, or specialized applications, involves considerations beyond just the material itself. Curved plates improve ergonomics and load distribution. The human torso is not flat. It curves, it moves, it flexes. Flat armor plates, while simpler to manufacture, don't conform well to the body. They create pressure points, they restrict movement, they shift and move uncomfortably during activity. Modern boron carbide armor plates are often manufactured with curves that match human anatomy. The plate might have a gentle convex curve matching the chest or back contour. This curvature is achieved during the pressing and sintering process. The green body is shaped in a curved die, and this curvature is maintained through sintering. The curved plate sits more naturally against the body, distributes its weight over a larger area, reducing pressure points, moves with the body more naturally during running or bending or prone positions. Comfort matters when armor must be worn for hours or days. An uncomfortable plate that digs into the shoulders or ribs, that shifts and moves, that causes pain. Such a plate might be removed by soldiers who can't tolerate the discomfort, defeating the protection entirely. Curved plates that fit well, that distribute their weight effectively, are more likely to be worn consistently, more likely to be properly positioned, more likely to fulfill their protective purpose when needed. And for vehicle applications, the geometry of armor coverage takes a different form. Hexagonal tiles cover vehicles efficiently. When armoring a vehicle surface, a door panel, a floor or wall, manufacturers must decide how to arrange the ceramic tiles. Individual tiles are typically kept relatively small, perhaps 50 to 100 millimeters across, so that damage from a single impact is localized to one tile rather than compromising a large panel. But how should these tiles be arranged? Square tiles leave gaps at edges unless cut precisely. Rectangular tiles can create weak points at corners where four tiles meet. Hexagonal tiles, six-sided tiles like honeycomb cells, offer advantages. They tile together efficiently with minimal gaps. Each tile is surrounded by 6 neighbors, distributing stress across more boundaries. There are no points where 4 corners meet, eliminating a potential weak point in the armor array. The hexagonal pattern allows complex curved surfaces to be covered more easily than with square tiles. The tiles can vary slightly in size and shape to accommodate curves while maintaining efficient coverage. When a hexagonal armor array is mounted to a vehicle backing plate and installed on a door or floor panel, the result is efficient protection coverage with controlled damage localization. Each hexagonal tile can be sacrificed to defeat a threat without compromising the protection provided by neighboring tiles. This attention to geometric efficiency, to tile arrangement and damage control, exemplifies the level of engineering sophistication that goes into modern armor systems. It's not enough to have remarkable material properties. Those properties must be implemented in system designs that account for practical realities of use, maintenance, damage tolerance, and effectiveness. And all of this engineering, all this careful design and manufacturing, all this accumulated knowledge and capability exists for one fundamental reason. These systems save lives every day. Not hypothetically, not potentially, actually measurably, documentably, these systems save lives. Soldiers struck by rifle fire, while wearing boron carbide body armor, walk away with bruises instead of fatal wounds. The ceramic plate cracks, fractures, does its job of defeating the projectile, and the soldier survives to continue the mission, to return home to family, to live beyond that moment of impact that would have been fatal without the protection. Vehicle crews survive IED attacks that would have killed them if their vehicle lacked the floor armor that absorbed and spread the blast energy. The boron carbide tiles on the floor shatter under the explosive force, but they prevent penetration, and the crew survives with injuries instead of dying in the blast. Helicopter pilots survive ground fire during insertions and extractions because the seat beneath them contains boron carbide plates that stop rounds coming up through the fuselage floor. The aircraft returns to base with bullet holes, with damaged tiles, but with a living pilot who can fly again. Police officers advance toward active shooters behind ballistic shields, confident that the boron carbide ceramic will protect them from the rifle rounds they might face, allowing them to close distance and neutralize the threat before more innocent people are killed. These are not abstract scenarios. These are events that happen regularly in conflicts and operations around the world. Each saved life represents a family that didn't receive a devastating notification, a unit that maintained its capability, a community that kept a protector, a person who gets to live the rest of their life instead of becoming a casualty statistic. The engineers who design these armor systems, the manufacturers who produce the ceramic with such care and precision, the researchers who continue to optimize and improve the materials. They may never meet the people their work saves. They may never know the specific instances where their ceramic stopped a bullet, where their design choices meant the difference between survival and death. But the lives are saved nonetheless. Every day, somewhere in the world, boron carbide armor fulfills its purpose. The dark ceramic, unassuming in appearance, proves its extraordinary capability in moments of extreme violence, turning aside threats through the mechanisms we've explored. The comminution, the debris cloud, the erosion and deflection. From Wausau's laboratory in 1894 to battlefields and operations worldwide today, boron carbide has traveled a long journey. From scientific curiosity to commercial abrasive to life-saving armor material, it has found its purpose in protection, in preservation of human life, in giving people facing danger a fighting chance to survive. The next time you see a soldier in body armor, a police tactical team with ballistic shields, an armored vehicle on patrol, remember that inside those protective systems, there might be tiles of boron carbide, dark and quiet, waiting for a moment that hopefully never comes, but ready to sacrifice themselves if it does, ready to turn violent kinetic energy into fine powder and save a life. This is the real-world impact of materials science, of understanding structure and properties, of manufacturing precision and engineering design. This is how knowledge transforms into protection, how atoms arranged in rhombohedral lattices save lives, how the careful control of grain size and stoichiometry translates into human survival. Boron carbide, the black diamond, the mysterious ceramic, it saves lives on the battlefield, and everywhere else protection is needed, every single day. We have celebrated boron carbide, its remarkable hardness, its lightweight, its life-saving capabilities. We have explored how it defeats rifle rounds, how it protects soldiers and vehicles, how it represents a triumph of materials science and engineering. But to truly understand any material, to use it wisely and effectively, we must also understand its limitations. Because every material, no matter how remarkable, has boundaries beyond which it cannot perform. Every design involves trade-offs, compromises, choices between competing properties. And boron carbide, for all its extraordinary capabilities, is no exception. Let us explore, with the same care and honesty we've applied to understanding its strengths, where boron carbide falls short, where its performance degrades, where other materials might be more appropriate choices. This is not a diminishment of boron carbide's value. Rather, it's an acknowledgement of reality, a recognition that engineering demands we understand both capabilities and limitations, that we choose materials wisely for their intended applications. And we should begin with perhaps the most significant limitation, the threat type where boron carbide's performance changes dramatically. Against long rod penetrators, performance drops. We've discussed how boron carbide defeats rifle rounds. Bullets with relatively blunt tips, short length-to-diameter ratios, traveling at velocities of 800 to 1,000 meters per second. Against these threats, boron carbide excels. The comminution mechanism, the debris cloud, the erosion and deflection, all work together effectively. But long rod penetrators are fundamentally different threats. These are armor-defeating projectiles used in tank warfare and heavy anti-armor weapons. They consist of extremely dense materials, typically tungsten alloy or depleted uranium, formed into long, slender rods with length-to-diameter ratios of 10 to 1, 15 to 1, or even higher. These penetrators travel at velocities that can exceed 1,500 or even 1,700 meters per second. They carry enormous kinetic energy concentrated into a small cross-section. And when they strike armor, they behave differently from rifle bullets. The long rod penetrator doesn't simply rely on its hardness or shape to penetrate. Instead, it enters a regime called hydrodynamic penetration, where the materials, both penetrator and armor, behave almost like fluids under the extreme pressures and strain rates of impact. The penetrator flows through the armor in a continuous process, eroding itself while also eroding and penetrating the target. Against such threats, boron carbide's performance is less impressive. The ceramic still comminuts, still creates a debris cloud, but the long rod penetrator has enough length and momentum to continue pushing through. The erosion that defeats shorter projectiles doesn't consume the entire length of the penetrator before it penetrates through the armor thickness. This doesn't mean boron carbide is useless against long rod penetrators. It still provides some resistance, still causes erosion, still contributes to defeating the threat, especially in multi-layered armor systems. But it's not the dominant armor choice for heavy armor applications where long rod penetrators are the primary threat. And there's a specific material level phenomenon that occurs at the extreme pressures created by long rod penetrator impact, a change in boron carbide's structure that compromises its effectiveness. Boron carbide undergoes localized amorphization. Amorphization is a term that describes the transition from crystalline structure to amorphous structure, from ordered to disordered, from that carefully arranged rhombohedral lattice we discussed earlier to a random, glass-like arrangement of atoms. Remember, boron carbide's strength and hardness come from its crystal structure, from the specific geometric arrangement of boron and carbon atoms, from the bonds between those atoms in their icosahedral clusters and connecting chains. This ordered structure resists deformation, provides the hardness that makes the debris cloud effective. But under extreme pressure, the kind of pressure created by long rod penetrator impact, where pressures can exceed 50 or even 100 gigapascals, the crystal structure becomes unstable. The atomic arrangements that are favorable at normal pressures become unfavorable at these extreme pressures. The structure collapses, transforms, becomes disordered. This happens very locally, very rapidly, in the region directly beneath the penetrator. The boron carbide, in that localized zone, loses its crystalline character and becomes amorphous, more like glass than like the original ceramic. And this transformation has consequences. This lowers density under extreme pressure. Counterintuitively, when boron carbide amorphizes under extreme pressure, it becomes less dense. The carefully packed crystal structure, with atoms positioned at specific locations dictated by bonding geometry, transforms into a disordered structure that actually occupies more volume per atom. Think about stacking oranges. If you stack them in an organized pattern, each orange nestled into the gaps between the oranges below, you can fit more oranges into a given space. But if you just pour oranges randomly into a box, they pack less efficiently, taking up more space for the same number of oranges. The amorphization of boron carbide is similar. The ordered structure packs more efficiently than the disordered structure. When the crystal structure is lost, the material expands slightly even while under compression. This expansion, this density decrease, reduces the material's resistance to penetration at that critical moment. The amorphized zone becomes a weak point, a region where the penetrator can more easily continue its advance. Instead of encountering the full hardness and strength of crystalline boron carbide, the penetrator encounters softer, less effective amorphous material. This amorphization phenomenon is specific to boron carbide, or at least, it occurs more readily in boron carbide than in some other ceramics under similar conditions. It's a fundamental limitation of the material structure, a consequence of the same complex atomic arrangements that provide its remarkable properties under less extreme conditions. And beyond the immediate impact zone, beyond the region of amorphization or comminution, there are other damage modes that limit boron carbide's effectiveness. Cracks propagate radially after impact. When a projectile strikes boron carbide, the immediate damage is the cone of comminuted ceramic directly beneath the impact point. But the stress waves from impact radiate outward through the entire tile, through neighboring tiles if they're in contact. These stress waves create tensile stresses, pulling forces, especially at the back surface of the tile and radiating outward from the impact point. And remember, ceramics are weak in tension. The boron carbide, while extremely strong in compression, fractures relatively easily when pulled apart. The result is radial cracking, cracks that extend outward from the impact point like spokes on a wheel. These cracks might extend several inches from the impact site, compromising material that wasn't directly struck, creating weakened zones that make subsequent impacts more likely to cause complete tile failure. In a perfect world, an armor tile would localize all damage to the immediate impact point, leaving the rest of the tile intact and capable of defeating additional threats. But the reality of stress wave propagation and ceramic brittleness means damage extends beyond the impact zone. This radial cracking is one reason why ceramic armor tiles are kept relatively small, to limit how far cracks can propagate before reaching a tile edge, where the crack can be arrested by the backing material or the gap between tiles. But even with small tiles and careful design, this damage propagation creates a serious practical limitation. Multi-hit capability is limited. In combat, threats rarely come as single shots with long intervals between them. Automatic weapons fire bursts of bullets in rapid succession. Multiple shooters might engage the same target. A vehicle might face continuous fire from several positions. Ideally, armor would defeat the first threat, and the second, and the third, all in the same location or near each other, without degradation in performance. But ceramic armor, including boron carbide, cannot do this indefinitely. The first impact creates the comminution zone, the radial cracks, the damaged region. A second impact close to the first, say, within a few inches, strikes material that's already cracked, already weakened. The ceramic can't comminute as effectively because it's already partially fragmented. The debris cloud is less dense, less effective. The erosion and deflection mechanisms work less well. After several impacts in close proximity, the armor in that region is essentially defeated. Additional rounds might penetrate where the first few were stopped. This is why armor testing standards specify not just single-shot defeats, but also multi-hit requirements. The armor must stop several rounds with specified spacing between impacts. Boron carbide performs well on these tests up to a point, but it cannot match the multi-hit capability of, say, steel armor, which deforms and absorbs impacts, but can continue providing some resistance across many more hits in the same area. For applications where concentrated fire is expected, where the same area might be struck repeatedly, this limited multi-hit capability must be considered in the armor design. Thicker tiles, overlapping coverage, sacrificial outer layers. Various design approaches attempt to mitigate this limitation. And when we compare boron carbide to other ceramic armor materials, we find that different ceramics make different trade-offs between properties. Silicon carbide is tougher but heavier. Silicon carbide, SiC, is another advanced ceramic used in armor applications. It shares some characteristics with boron carbide: extreme hardness, good temperature resistance, ceramic nature. But it differs in important ways. Silicon carbide has higher fracture toughness than boron carbide. Fracture toughness measures a material's resistance to crack propagation. Once a crack starts, how easily does it travel through the material? Higher toughness means cracks propagate less readily. Absorbed energy is dissipated over larger volumes. Catastrophic fracture is less likely. This higher toughness gives silicon carbide some advantages. It might show less radial cracking from impacts. It might maintain integrity better under certain loading conditions. It might provide better multi-hit performance in some scenarios. But silicon carbide is denser than boron carbide, approximately 3.2 grams per cubic centimeter compared to boron carbide's 2.5. That's roughly 28% heavier for the same volume. In weight-sensitive applications, body armor, aircraft protection, anywhere that mobility matters, this weight penalty is significant. So the choice between boron carbide and silicon carbide involves trade-offs. Do you prioritize minimum weight and accept somewhat lower toughness? Or do you prioritize better crack resistance and accept higher weight? Different applications demand different choices. And there's an even more dramatic trade-off available with another ceramic material. Alumina is cheaper, but much heavier. Aluminum oxide Al2O3, is the most widely used ceramic armor material. It's less hard than boron carbide or silicon carbide, but it's considerably less expensive to manufacture. The raw materials are cheaper, the processing temperatures are somewhat lower, the manufacturing is more established and optimized. For applications where cost is paramount, where budget constraints are severe, alumina provides a practical armor solution. It's effective against many threats, especially when used in sufficient thickness with proper backing. But alumina's density is approximately 3.9 grams per cubic centimeter, roughly 56% heavier than boron carbide for the same volume. This is a substantial weight penalty. An armor system using alumina tiles instead of boron carbide tiles of equivalent protection would weigh significantly more. For vehicle armor, where a few hundred pounds of additional weight might be tolerable, this trade-off can make sense. Save significant cost by accepting moderate weight increase. But for body armor, for aircraft, for any application where weight is critical, alumina's density becomes prohibitive despite its cost advantage. The armor industry uses all three ceramics, boron carbide, silicon carbide, and alumina, selecting among them based on the specific requirements of each application. Weight budget, cost constraints, threat types, multi-hit requirements all factor into the choice. And underlying all of these trade-offs, all these comparisons between ceramics, is a fundamental characteristic of boron carbide that influences every aspect of its performance and use. Boron carbide is brittle by nature. Brittleness means the material fractures without significant plastic deformation. It doesn't bend, doesn't stretch, doesn't absorb energy through ductile yielding like metals do. When stressed beyond its strength, it simply breaks. This brittleness is intrinsic to boron carbide's nature as a covalently bonded ceramic. The strong, directional bonds between atoms don't allow the kind of atomic rearrangement that enables plastic deformation in metals. The crystal structure is rigid, strong in its preferred loading directions, but unable to accommodate deformation. For armor applications, we've seen how this brittleness is actually advantageous. The comminution mechanism relies on the ceramic breaking into fine particles. But brittleness creates challenges in other contexts. Handling boron carbide requires care. Dropping a tile can crack it. Impacts during installation or maintenance can cause damage. Edges are vulnerable to chipping. The material cannot tolerate point loads or concentrated stresses without fracturing. Manufacturing must account for brittleness. Machining must be done carefully with appropriate diamond tools and techniques to avoid cracking. Tiles must be packaged and shipped with adequate protection. Installation procedures must ensure even support, avoiding stress concentrations that could crack the ceramic. And in armor system design, the brittleness influences every choice. How tiles are attached, how they're supported, how they're retained after impact, how backings are configured to prevent fragmentation from becoming a hazard. This brittleness is fundamental, unchangeable. You cannot make boron carbide ductile without changing what it fundamentally is. But you can sometimes choose different materials where different properties are prioritized. Designers sometimes trade hardness for toughness. In materials selection, there's often an inverse relationship between hardness and toughness. The hardest materials tend to be brittle: diamond, boron carbide, silicon carbide, tungsten carbide. Tougher materials tend to be softer: steels, titanium alloys, aluminum alloys. When designing an armor system, engineers must decide which property matters more for the specific threat and application. Against hard, sharp-nosed armor-piercing bullets, extreme hardness like boron carbide might be essential to defeat the threat. But against blunt impacts, fragmentation, or situations where the armor must endure multiple impacts and rough handling, tougher materials might perform better overall even if they're less hard. Some armor systems use layered approaches: an outer layer of extremely hard ceramic like boron carbide to defeat sharp projectiles, backed by tougher materials that catch fragments and absorb energy. This combines the advantages of both material types. Other systems might forego boron carbide entirely if the threat doesn't require its extreme hardness, choosing instead steel or titanium armor that's tougher, easier to manufacture, more tolerant of rough handling and maintenance. The key is matching material properties to application requirements, understanding that no single material excels at everything. Which brings us to perhaps the most important perspective to maintain about boron carbide, or any armor material. No armor material is perfect. This is a simple statement, but it's worth reflecting upon. Despite all the engineering sophistication, all the materials science knowledge, all the manufacturing precision, there is no perfect armor material that provides maximum protection at minimum weight with no limitations or trade-offs. Boron carbide is extraordinary in many ways. Its hardness-to-weight ratio is exceptional. Its performance against rifle threats is excellent. Its applications have saved countless lives. But it undergoes amorphization under extreme pressure. It has limited multi-hit capability. It's brittle and requires careful handling. It's expensive to manufacture. Silicon carbide offers better toughness, but weighs more. Alumina costs less, but weighs much more. Steel is tough and cheap, but heavy and less effective against hard projectiles. Titanium is light and tough, but expensive and doesn't match ceramic hardness. Every material represents a set of compromises. Every application requires choosing which properties matter most and accepting the limitations that come with that choice. The engineer's job is not to find the perfect material. Such a material doesn't exist. The job is to understand the requirements, understand the materials, and make informed choices that optimize the overall system performance, even while accepting that some individual properties will be less than ideal. Boron carbide, with all its remarkable capabilities and all its limitations, is a tool in the armor designer's toolbox. Sometimes it's the right tool for the job. Sometimes other materials are more appropriate. Wisdom lies in knowing the difference, in understanding deeply enough to choose well. As we've explored boron carbide's limitations, its challenges with long rod penetrators, its amorphization under extreme pressure, its crack propagation and limited multi-hit capability, its trade-offs compared to other ceramics, its fundamental brittleness, we haven't diminished the material. Rather, we've gained a more complete understanding, a more honest appreciation of what it is and what it can do. Boron carbide remains one of the most remarkable armor materials available. But it's not magic. It's not unlimited. It's a material with extraordinary properties and real limitations, suited to some applications and less suitable to others, capable of saving lives when used appropriately and understanding its bounds. This honest assessment, This recognition of both capabilities and limitations is essential to using any material wisely, to designing systems that perform reliably, to protecting the people who depend on that protection. We have explored boron carbide primarily as an armor material. Its role in defeating projectiles, protecting lives, serving as a barrier between danger and those who face it. But remarkable materials with extraordinary properties, rarely find themselves limited to a single application. Their unique characteristics open doors to uses that might seem unrelated at first glance, that draw on different aspects of their nature, that solve problems in entirely different fields. Boron carbide is no exception. Beyond the battlefield, beyond armor plates and ballistic shields, this dark ceramic serves in roles that would surprise anyone who knows it only as a protective material. Let us explore these unexpected applications, these other lives that boron carbide lives, these problems it solves that have nothing to do with stopping bullets. And we should begin with a property of boron carbide that has nothing to do with hardness or density, but rather with nuclear physics. Boron carbide absorbs neutrons efficiently. Neutrons are subatomic particles, components of atomic nuclei alongside protons. They carry no electrical charge, which makes them difficult to shield against. Where charged particles like protons or electrons can be deflected by electric or magnetic fields, neutrons simply pass through such fields unaffected. But neutrons can be absorbed by certain atomic nuclei. When a neutron collides with a nucleus capable of capturing it, the neutron is absorbed. The nucleus transforms into a different isotope or element, and the neutron is removed from circulation. This neutron absorption capability becomes critically important in nuclear reactors and other applications involving nuclear reactions. In a nuclear reactor, neutrons are what sustain the chain reaction. Neutrons released by one fission event go on to trigger additional fission events. Controlling the neutron population, controlling how many neutrons are available to cause fission, is fundamental to controlling the reactor's power level. Boron carbide absorbs neutrons with remarkable efficiency. When neutrons encounter boron carbide, many are captured and removed from the neutron population. This makes boron carbide valuable anywhere neutron control is needed. But not all boron is equally good at neutron absorption. The property depends on a specific variant of boron. The boron 10 isotope is key to this property. Boron exists naturally as a mixture of two stable isotopes, boron 10 and boron 11. Isotopes are variants of an element with different numbers of neutrons in the nucleus. Boron 10 has 5 protons and 5 neutrons, while boron 11 has 5 protons and 6 neutrons. Natural boron is approximately 20% boron 10 and 80% boron 11. But these two isotopes have vastly different neutron absorption capabilities. Boron 10 has an enormous neutron capture cross-section. It's extraordinarily effective at absorbing neutrons. Boron 11, by contrast, has very low neutron absorption. So when we say boron carbide absorbs neutrons efficiently, we're really saying that the boron 10 within boron carbide absorbs neutrons efficiently. The more boron 10 present, the more effective the neutron absorption. This has led to specialized forms of boron carbide, where the isotopic composition is controlled, where the natural ratio is altered to increase boron 10 content for applications requiring maximum neutron absorption, or conversely, reduced for applications where neutron absorption is undesirable. And the most prominent application of boron carbide's neutron absorption capability is in nuclear reactor control. It's used in nuclear control rods. Nuclear reactors need mechanisms to control their power level, to shut down safely, to maintain stable operation. Control rods serve this purpose. Rods containing neutron-absorbing materials that can be inserted into or withdrawn from the reactor core. When control rods are fully inserted into the core, they absorb large numbers of neutrons, reducing the neutron population available to sustain fission, reducing the reactor's power level, or even shutting it down entirely. When control rods are withdrawn, fewer neutrons are absorbed, allowing the chain reaction to intensify and power to increase. Boron carbide is a common material for control rods, especially in certain reactor designs. The control rods might be made of boron carbide pellets encased in metal cladding, or boron carbide powder contained in metal tubes, or various other configurations depending on the reactor type. The advantages of boron carbide for this application include its high neutron absorption, especially if enriched in boron-10, its thermal stability, allowing it to function at reactor operating temperatures, its chemical stability, preventing unwanted reactions with coolant or other reactor materials, and its physical form as a ceramic that can be fabricated into the needed shapes. Nuclear reactors around the world, generating electricity that powers cities and industries, rely on boron carbide control rods to operate safely and stably. The same material that stops bullets in armor also stops neutrons in reactor cores. Two completely different applications, two completely different properties being utilized. And the dual nature of boron carbide, useful both for armor and for nuclear applications, creates an interesting manufacturing consideration. Some armor grades control isotopic composition. For armor applications, neutron absorption is irrelevant. Bullets don't involve nuclear reactions. There are no neutrons to absorb on a battlefield. The isotopic ratio of boron, 10 to boron, 11 makes no difference to ballistic performance. But natural boron contains that 20% boron-10. And in certain environments, particularly around nuclear facilities, or in specialized applications where the armor might be exposed to neutron radiation, the presence of boron-10 could create issues. When boron-10 absorbs a neutron, it undergoes a nuclear reaction that releases alpha particles and gamma radiation. This could create a radiation hazard or complicate radiation monitoring. For these specialized applications, boron carbide armor might be manufactured using boron depleted in boron-10. Boron with a natural isotopic ratio has been altered to contain less boron-10 and more boron-11. This depleted boron carbide provides the same ballistic protection while minimizing neutron absorption and the associated radiation emissions. Conversely, for nuclear shielding applications, boron carbide might be enriched in boron-10 to maximize neutron absorption efficiency. The same base material, boron carbide, can be tailored at the isotopic level to suit different applications, demonstrating the sophistication of modern materials manufacturing and the care taken to optimize materials for specific uses. But beyond nuclear applications, beyond armor, boron carbide finds extensive use in industrial contexts that rely on its extreme hardness and wear resistance. It's used in blast nozzles and slurry pumps, in industrial operations involving abrasive materials, sandblasting, slurry pumping, particle transport. Components experience severe wear. Sand particles, mineral slurries, abrasive powders constantly grind against nozzle walls, pump impellers, pipe linings, wearing away material, causing failures, requiring frequent replacement. Traditional materials for these components, steels, even hardened steels, wear relatively quickly under such conditions. A steel blast nozzle might last hours or days before wearing to the point where it must be replaced. A pump handling abrasive slurry might need impeller replacement every few weeks. Boron carbide, with its exceptional hardness, resists this abrasive wear far more effectively. A blast nozzle lined with boron carbide might last months instead of days, handling thousands of hours of abrasive blasting before wear necessitates replacement. Pump components made with boron carbide linings or inserts resist slurry erosion, maintaining their efficiency and requiring replacement far less frequently. The economics are compelling. Boron carbide components are more expensive initially, sometimes much more expensive than steel equivalents. But if a boron carbide part lasts 50 or 100 times longer than a steel part, the cost per unit of service life becomes favorable. And the reduced downtime for component replacement, the labor savings from less frequent maintenance, the consistent performance over longer periods. These factors often justify the higher initial cost. Industrial facilities worldwide use boron carbide components precisely where wear is most severe, where component life is critical, where the cost of failure or frequent replacement is high. This brings us to a broader category of boron carbide applications, based on its wear resistance. Abrasive applications extend component lifespan. Beyond blast nozzles and pumps, boron carbide serves in numerous applications where its hardness provides extended service life. Grinding media, the balls or cylinders used in ball mills to pulverize materials, can be made from boron carbide for applications requiring contamination-free grinding, where the grinding media itself must resist wear and not contaminate the material being ground. Cutting tools for specialized applications, particularly for cutting other hard materials, sometimes incorporate boron carbide. Wire drawing dies, where metal wire is pulled through progressively smaller openings to reduce its diameter, can use boron carbide inserts to resist the wear from thousands or millions of cycles. Seal faces in mechanical seals, where two surfaces must slide against each other while maintaining a pressure seal, sometimes use boron carbide for its combination of hardness and chemical resistance. The seal faces maintain their flatness and finish over extended operation, providing reliable sealing in pumps and rotating equipment handling aggressive fluids. In each case, the principle is the same. Boron carbide's extreme hardness translates to exceptional wear resistance, which translates to extended component life, which translates to reduced maintenance costs and improved operational reliability. And the wear resistance enables another advantage beyond just longevity. It allows thinner, lighter wear parts. Because boron carbide resists wear so effectively, components can be designed with less material, thinner cross-sections, reduced weight, while still achieving acceptable service life. A steel liner might need to be 10 mm thick to provide adequate wear life. A boron carbide liner providing equivalent, where life might be only 3 or 4 mm thick. This thickness reduction saves weight, saves material cost, even though boron carbide itself is expensive per kilogram. Using less total material can offset this, and can enable designs that wouldn't be possible with thicker components. A rotating part that must be precisely balanced benefits from thinner, lighter wear-resistant surfaces. A component with limited space for where parts benefits from the reduced thickness requirements. The same principle we saw in armor, achieving performance goals with reduced weight, applies in industrial wear applications. The material properties that enable lightweight armor also enable efficient, long-lasting industrial components. But working with boron carbide, whether in manufacturing armor or industrial components, requires awareness of safety considerations that don't apply to many other materials. Powder handling requires dust control for safety. Boron carbide powder, the fine black powder we've discussed throughout this series, is a dust. And like many fine dusts, it poses inhalation hazards. Breathing boron carbide dust is not acutely toxic in the way some chemical dusts are, but any fine particulate in the lungs is problematic. The particles can cause irritation, can accumulate in lung tissue, can potentially contribute to long-term respiratory issues. Additionally, some fine powders can form explosive dust clouds under the right conditions. While boron carbide is not particularly prone to dust explosions compared to some materials, any fine powder in sufficient concentration in air presents some explosion risk if an ignition source is present. Manufacturing facilities that handle boron carbide powder must implement dust control measures. Local exhaust ventilation at grinding and handling stations, enclosed processes where possible, personal protective equipment including respirators for workers, proper storage to prevent dust accumulation, housekeeping procedures to clean up any spilled powder before it can become airborne. These safety considerations add complexity and cost to boron carbide processing, but they're necessary to protect workers and maintain safe operations. The material that protects soldiers and enables industrial applications must itself be handled with care and respect during manufacturing. And beyond powder handling, working with finished boron carbide components presents its own challenges, particularly when modification or machining is needed. Laser cutting dense tiles is difficult. Many materials can be cut efficiently with laser cutting. The focused laser beam melts or vaporizes material along the cut line, producing clean, precise cuts with minimal mechanical stress on the workpiece. For metals, polymers, even some ceramics, laser cutting is an attractive fabrication method. But boron carbide's extreme melting point, exceeding 3000 degrees Celsius, remember, makes laser cutting challenging. The laser must deliver enough energy to heat the material to these extreme temperatures. The process is slow. Thermal stresses from the intense local heating can cause cracking in the ceramic. The quality of the cut edge may not be acceptable for precision applications. Some advanced laser systems can cut boron carbide, but it's not an easy or routine process. The cutting is typically slow, requires high-power lasers, may produce cracking or edge damage that necessitates additional finishing operations. For many applications, laser cutting simply isn't practical for boron carbide. Other methods must be used to shape and cut the material. Fortunately, there are alternative machining techniques specifically suited to ultra-hard ceramics. Ultrasonic machining enables complex shapes. Ultrasonic machining is a process quite different from conventional cutting or grinding. Instead of a sharp tool that cuts by being harder than the workpiece, ultrasonic machining uses a tool that vibrates at ultrasonic frequencies, typically 20,000 to 40,000 vibrations per second, while a slurry of abrasive particles flows between the tool and workpiece. The vibrating tool doesn't cut the boron carbide directly. Instead, the vibration causes the abrasive particles in the slurry to repeatedly impact the workpiece surface, chipping away tiny fragments with each impact. Thousands of microscopic impacts per second gradually erode the ceramic, removing material in the shape defined by the tool. This process can create complex shapes, holes, slots, intricate contours, in boron carbide that would be impossible or impractical with conventional machining. The process is relatively slow compared to machining metals, but it's reliable, produces good surface quality, and can work with extremely hard materials that defeat other machining methods. Ultrasonic machining allows manufacturers to create complex boron carbide components, armor plates with precisely positioned mounting holes, nozzles with intricate internal passages, components with features that can't be formed during the initial pressing and sintering process. Combined with diamond grinding for external surfaces and conventional pressing/sintering for basic shapes, ultrasonic machining completes the toolkit that allows boron carbide to be fabricated into the diverse forms required by its many applications. And this diversity of applications, this range of uses from nuclear control rods to blast nozzles to armor plates, speaks to the fundamental versatility of remarkable materials. Boron carbide was discovered as a laboratory curiosity. It found early commercial use as an abrasive. It proved its worth in armor applications. It serves critical roles in nuclear reactors. It extends equipment life in industrial settings. Each application draws on different properties: hardness for wear resistance, neutron absorption for nuclear control, hardness to weight ratio for armor, thermal stability for high temperature applications. Some applications use natural boron carbide. Others require isotopically controlled compositions. Some use fine powder. Others use dense sintered shapes. The material adapts, serves, performs across this range of applications because its fundamental properties, that rhombohedral crystal structure, those strong covalent bonds between boron and carbon, that combination of light atomic weight and complex structure, provide a portfolio of useful characteristics. This is the nature of advanced materials. They solve not one problem, but many. They enable not one application, but numerous applications. They reward our understanding and careful manufacture by serving human needs across diverse fields, from protection to industrial efficiency to nuclear energy. Boron carbide, the black diamond, the mysterious ceramic weave explored from its atomic structure to its real-world uses, continues to surprise, continues to find new applications, continues to demonstrate that materials with truly exceptional properties never run out of ways to be useful. We have traveled a long journey together, through the world of boron carbide. From Henri Moissan's laboratory in 1894 to modern battlefields and industrial facilities, from atomic structures to ballistic impacts, from limitations to unexpected applications, we have explored this material from every angle, examined its triumphs and its constraints, understood both what it can do and what it cannot. But our journey should not end with the present. Materials science does not stand still. Every material we use today, no matter how advanced, is merely a stepping stone toward tomorrow's materials. And boron carbide, for all its remarkable properties, for all its current success, is not a finished story. It is an evolving one. Let us conclude our exploration by looking forward, by considering where boron carbide is heading, how researchers are improving it, how manufacturers are optimizing it, how the future of this black diamond continues to unfold. Researchers explore doped and composite boron carbide. Pure boron carbide, as we've discussed extensively, has an extraordinary set of properties. But what if we could modify those properties slightly? What if we could add elements, create composites, engineer the material at ever finer scales to enhance certain characteristics while maintaining the advantages we value? This is the frontier of boron carbide research. Not replacing the material entirely, but augmenting it, optimizing it, creating variants that perform even better for specific applications. Doping means intentionally adding small amounts of other elements to the boron carbide structure. Perhaps adding titanium, or aluminum, or other elements that can substitute into the crystal lattice or occupy positions at grain boundaries. These dopants can alter properties, potentially improving toughness by changing how cracks propagate, or modifying thermal properties, or enhancing sinterability to achieve higher densities with less extreme processing conditions. Composite approaches involve combining boron carbide with other materials at various scales. Perhaps mixing boron carbide powder with silicon carbide powder before sintering, creating a material that contains both ceramics, potentially combining the best properties of each. Or creating layered structures where different compositions alternate in thin layers, engineered to manage stress waves or provide graduated properties. These are not random experiments. They're guided by increasingly sophisticated understanding of how atomic scale structure influences macroscopic properties, by computational models that can predict how changes will affect performance, by systematic exploration of composition space seeking optimal combinations. And one particularly promising direction combines boron carbide with its ceramic cousin. Silicon carbide hybrids improve toughness. We discussed earlier how silicon carbide offers higher toughness than boron carbide, but at a weight penalty. What if we could combine them, creating a hybrid material that captures advantages of both? Researchers have developed boron carbide silicon carbide composites, where silicon carbide forms a secondary phase within a boron carbide matrix, or vice versa. The silicon carbide regions can help arrest cracks, can provide tougher paths that absorb energy when the material is stressed, can reduce the brittleness that pure boron carbide exhibits. The resulting hybrid materials show improved damage tolerance. They still comminate under ballistic impact, still provide the hardness needed for projectile defeat, but they may show reduced radial cracking, improved multi-hit capability, better resistance to handling damage. The challenge is controlling the microstructure, ensuring the two ceramics distribute properly, optimizing the ratio to achieve the desired property balance. Too much silicon carbide, and the weight advantage is lost. Too little, and the toughness improvement is negligible. But within the right compositional range, hybrids offer measurable performance improvements. This represents the kind of incremental but important progress that advanced materials undergo. Not revolutionary changes, but steady optimization, careful engineering to extract every possible advantage from the fundamental chemistry and physics. And improvements come not just from changing composition, but from controlling the material at ever finer scales. Nano-sized powders improve sintering quality. The boron carbide powders we've discussed typically have particle sizes measured in micrometers, millionths of a meter. But what if we could make powders where particles are measured in nanometers, billionths of a meter, 1,000 times smaller? Nano-sized powders, with their extremely small particle size, have vastly more surface area per unit mass than conventional powders. This high surface area makes them more reactive, more sinterable. They can consolidate to full density at lower temperatures, or in shorter times than conventional powders require. Additionally, starting with nano-sized powders can result in finer grain sizes in the final sintered material. Remember our discussion of grain size control and its importance for armor performance? Nano powders offer a pathway to even finer, more controlled microstructures than are easily achieved with conventional powders. The challenges are significant. Nano powders are difficult to handle. They agglomerate easily. They're even more prone to forming dust clouds. They require special processing to prevent contamination. Synthesizing boron carbide at the nanoscale requires different approaches than conventional manufacturing. But the potential improvements in sintered density, microstructure control, and potentially even in new property combinations make this an active area of research. As manufacturing techniques mature, as researchers learn to handle and process nanoscale boron carbide powders effectively, we may see the next generation of armor materials emerging from these ultra-fine starting materials. And improvements come not just from the material itself, but from how we configure it into armor systems. Graded armor stacks manage shock waves. When a projectile strikes armor, it creates stress waves, pressure waves that propagate through the material at the speed of sound in that material. These stress waves can reflect off interfaces between different materials, can interact constructively or destructively, can create complex stress states that influence how the armor responds. Graded armor takes advantage of this by creating layered structures where properties change gradually rather than abruptly. Perhaps a front layer of extremely hard boron carbide, backed by a layer with slightly lower hardness but better toughness, backed by progressively tougher materials, each layer optimized for managing a different phase of the impact event. The hard front layer defeats the projectile tip through the mechanisms we've discussed. The intermediate layers manage the stress waves, absorb energy, prevent catastrophic crack propagation. The backing layers catch fragments, spread loads, provide structural integrity. By carefully selecting materials, thicknesses, and arrangements, engineers can create armor stacks that perform better than single material armor of equivalent weight. The system becomes greater than the sum of its parts, with each layer contributing its optimal characteristics at the right moment in the impact sequence. Computational modeling plays a crucial role in designing these graded structures, allowing engineers to simulate impact events and optimize layer arrangements before expensive physical testing. And computational approaches are transforming other aspects of armor design as well. Computational models optimize tile layouts. We've discussed how armor uses multiple tiles rather than single large plates, how hexagonal tiles offer efficient coverage, how tile size and arrangement affect damage containment and multi-hit performance. But determining the optimal tile layout for a specific application, what size tiles, what spacing, what arrangement pattern, what edge treatments, has traditionally required extensive testing, trying different configurations and evaluating their performance. Now, sophisticated computer models can simulate ballistic impacts against various tile configurations, predicting how damage propagates, how stress waves interact with tile boundaries, how different arrangements perform against single hits and multiple hits at various spacings. These models allow engineers to explore hundreds or thousands of configuration options virtually, narrowing down to the most promising candidates before committing to expensive physical testing. The models don't eliminate testing. Real-world validation remains essential, but they dramatically accelerate the design process and increase confidence that the tested configurations will perform well. As these computational tools become more sophisticated, as they incorporate better physics models and more detailed material data, they increasingly enable optimization that would be impossible through testing alone. The future of armor design is increasingly digital, with computer simulation, guiding physical development. But looking forward isn't only about improving performance. Sustainability, resource efficiency, and economics also matter increasingly in materials development and use. Recycling post-impact fragments can recover 80% of value. When boron carbide armor defeats a projectile, the tile is damaged, comminuted in the impact zone, cracked radially, no longer suitable for armor use. Traditionally, these damaged tiles might be discarded, sent to landfills, treated as waste. But boron carbide is valuable. The material itself, even in fragmented form, still consists of boron and carbon in approximately the right ratio. If the fragments can be collected, crushed back to powder, purified to remove any contamination from projectile residue or backing materials, they can potentially be recycled back into the manufacturing process. Researchers have demonstrated that post-impact boron carbide fragments can be reprocessed into powder suitable for sintering into new tiles. The recycled powder may not be identical to virgin powder. There might be subtle composition variations, grain size differences, contamination that must be removed. But with appropriate processing, recycled boron carbide can recover perhaps 80% of the material's value, dramatically reducing the effective cost of armor over its life cycle. This recycling is particularly valuable for training and testing, where large quantities of armor are deliberately shot to validate performance or train personnel. Instead of all that material being waste, a substantial fraction can return to the manufacturing stream, making the economics of extensive testing more favorable. As sustainability becomes increasingly important in material selection and use, the ability to recycle expensive materials like boron carbide strengthens its position as a preferred armor material. The high initial cost is partially offset by recovery value, making the total life cycle cost more competitive. Speaking of cost, let us consider the economics that influence where and how boron carbide is used. Production costs range from $50 to $100 per kilogram. $50 to $100 per kilogram. This is the typical cost range for armor-grade boron carbide powder. To put this in perspective, steel costs perhaps $1 or $2 per kilogram. Even advanced aluminum alloys might cost $5 to $10 per kilogram. Boron carbide is expensive, typically 10 to 20 times the cost of conventional armor materials by weight. This cost reflects the energy-intensive manufacturing we've discussed, the extreme temperatures, the specialized equipment, the careful quality control, the expensive raw materials, the multiple processing steps from synthesis through crushing and purification. Every kilogram of armor-grade boron carbide represents significant manufacturing investment. But remember the weight advantage. If boron carbide armor is 1/3 the weight of steel armor, providing equivalent protection, then even at 20 times the cost per kilogram, it's only about 7 times the cost per armor system. And when you factor in the operational advantages, better mobility, reduced vehicle fuel consumption, less soldier fatigue, the cost premium becomes more justifiable for applications where these factors matter. For vehicle armor on main battle tanks where weight is less critical, the cost might not be justified. But for body armor, for aircraft, for light vehicles where weight is paramount, the cost premium is acceptable and often necessary to achieve the required performance. Market forces continue to drive costs down slowly as manufacturing improves, as economies of scale increase with growing demand, as competition among suppliers intensifies. But fundamental physics and chemistry limit how much costs can decrease. The extreme temperatures will always require significant energy. The careful quality control will always add cost. The specialized equipment will always be expensive. Future cost reductions will likely come from manufacturing efficiency improvements rather than from fundamental breakthroughs, with costs perhaps gradually decreasing to the $30 to $50 per kilogram range over coming decades for high-volume applications. And the economics of boron carbide are intertwined with national security considerations. Supply chains are considered strategically critical. Boron carbide is not just another industrial commodity. It's a critical defense material, essential for protecting military personnel and equipment. Nations that cannot produce their own boron carbide must import it, creating dependence on foreign suppliers that could be problematic during conflicts or international tensions. Governments recognize boron carbide supply chains as strategically important. Domestic production capability is valued even if imported material might be cheaper. Stockpiles may be maintained to ensure availability during emergencies. Manufacturers of armor-grade boron carbide may receive government support or protection. The raw materials, boron sources and carbon, also receive strategic attention. Boron minerals are not uniformly distributed globally. Major deposits exist in Turkey, the United States, Argentina, Chile, and a few other locations. Nations want to ensure access to these raw materials, either through domestic deposits or reliable trade relationships. As global tensions evolve, as supply chain vulnerabilities become more apparent, expect increasing attention to boron carbide production capacity, to raw material security, to domestic manufacturing capability. The material that protects soldiers is itself considered an asset worth protecting and securing. This strategic importance has driven consistent investment in boron carbide technology and production capacity over decades, ensuring that the material remains available for critical defense applications. And this investment has paid dividends in deployed systems that protect personnel every day. SOP plates have used boron carbide since the early 2000s. SOP stands for Enhanced Small Arms Protective Insert, the ceramic armor plates used by US military personnel in their body armor systems. These plates, inserted into pouches in soft armor vests, provide protection against rifle threats that the soft armor alone cannot stop. Since the early 2000s, many SOP plates have used boron carbide as their ceramic component. The exact designs are often classified, but publicly available information confirms that boron carbide has been a primary ceramic choice for these life-saving armor plates. Hundreds of thousands of these plates have been manufactured and issued. They've been worn in combat operations in Iraq, Afghanistan, and other theaters. They've stopped bullets, saved lives, proven their effectiveness in the ultimate test, actual combat use. The continued use of boron carbide in SOP plates over more than 2 decades, through multiple design iterations and improvements, demonstrates confidence in the material's performance. If better alternatives existed at acceptable cost and weight, the military would adopt them. The persistence of boron carbide in these critical armor systems speaks to its unique combination of properties that remain difficult to match with other materials. Service members around the world trust their lives to these plates, to the boron carbide ceramic within them, to the engineering and manufacturing precision that ensures they'll perform when needed. This trust has been earned through rigorous testing, through combat validation, through the saved lives of those who were struck, but survived because their armor worked. And this brings us to the final reflection on boron carbide, to the ultimate assessment of this material we've explored so thoroughly. The black diamond remains one of armor's greatest materials. More than 130 years after Henri Moissart first synthesized it in his electric arc furnace, boron carbide endures as a critical material for protection. It has survived the test of time, proven its value across changing threats and evolving requirements, maintained its position despite continuous research into alternative materials. Why has it endured? Because its fundamental properties, that exceptional hardness-to-weight ratio, that ability to comminate and create erosive debris clouds, that chemical and thermal stability, that resistance to wear and corrosion. These properties arise from its atomic structure, from the nature of boron and carbon bonded in rhombohedral lattices, from fundamental physics and chemistry that don't change with time or fashion. New materials will continue to be developed. Researchers will create novel ceramics, composites, hybrid structures. Some may offer incremental improvements in specific properties, but displacing boron carbide entirely from armor applications would require a material that matches or exceeds its performance across the full range of requirements. Hardness, density, manufacturability, cost, availability, proven reliability. Such materials are rare. Diamond is harder, but far more expensive and difficult to manufacture in usable forms. Other ceramics offer different trade-offs, but not clear superiority. Composite approaches may enhance certain properties, but add complexity and cost. So boron carbide persists, evolves gradually through incremental improvements, continues serving as a primary armor material for applications where its strengths align with requirements. Looking forward, we can expect continued refinement of manufacturing processes, achieving better microstructure control, higher densities, more consistent properties batch to batch, development of hybrid and composite materials that combine boron carbide with other ceramics or phases to enhance specific properties like toughness while maintaining weight advantages. Advanced computational design tools that optimize armor configurations, predict performance more accurately, reduce development time and cost. Growing attention to sustainability and recycling, recovering value from used armor, reducing the environmental footprint and economic cost of protection. Expanding applications beyond traditional armor, perhaps in space applications where weight is critical and radiation protection is valuable, in advanced industrial equipment requiring extreme wear resistance, in new contexts we haven't yet imagined. But through all these developments, through all this evolution and improvement, boron carbide will remain fundamentally what it is: a ceramic compound of boron and carbon, hard and light, brittle but effective, expensive but valuable, discovered in 1894 and still saving lives in 2026. The black diamond, the mysterious ceramic that looks unassuming but performs extraordinarily. The material that breaks to protect, that sacrifices itself to save others, that embodies in its atomic structure the possibility of protection without crushing burden. As we conclude our exploration, as we step back from the details of crystal structures and ballistic impacts and manufacturing processes, let us remember the fundamental purpose that drives all this science and engineering: preserving human life. Every refinement in boron carbide processing, every improvement in armor design, every advancement in understanding how the material defeats threats, all of it serves that single purpose: to give people facing danger a better chance of survival, to make protection more effective and more practical, to enable those who serve and protect to do so with greater safety. Materials science can seem abstract, divorced from human concerns, focused on properties and processes and technical details. But materials like boron carbide remind us that science serves humanity, that understanding nature at the deepest levels enables us to create things that matter, that preserve what is precious. The soldier wearing body armor with boron carbide plates may never know the material's history, may never understand its crystal structure or the mechanisms by which it defeats projectiles. But in that critical moment when a bullet strikes, when the ceramic culminates and creates its debris cloud, when the erosion and deflection mechanisms work exactly as designed, when the soldier feels the impact but survives, in that moment, all the science and engineering and manufacturing precision justify themselves completely. This is the legacy of boron carbide. This is the story of the black diamond, a material discovered as a curiosity, developed for industry, perfected for protection, serving faithfully wherever hardness and light weight must combine, saving lives not just occasionally, but continuously, every day, around the world. And its story continues. Researchers in laboratories are exploring new variants even now. Manufacturers are producing powder and sintering tiles that will become armor. Engineers are designing the next generation of protective systems. Service members and law enforcement officers are wearing armor that contains this remarkable ceramic, trusting it to protect them. The future of the black diamond is not yet written, but it will be forged in the same way its past has been. Through careful science, through engineering precision, through the dedication of those who recognize that materials matter, that protection saves lives, that understanding nature allows us to create things of extraordinary value. Boron carbide, B4C, 4 boron atoms, 1 carbon atom, arranged in patterns of atomic perfection, hard and light, brittle but effective, expensive but invaluable. The black diamond endures, serves, protects, and will continue doing so for as long as humans need armor, need protection, need materials that can save lives when it matters most. This is the story we've explored together. This is the material we've come to understand. And this understanding, this appreciation for what boron carbide is and how it serves, is itself valuable. Because informed appreciation of the materials that protect us, of the science and engineering that makes that protection possible, connects us to the reality that preservation of life depends on knowledge, on precision, on the careful application of understanding to practical purposes. May the black diamond continue its service. May those who depend on it for protection find that protection reliable and effective. And may we continue to refine, improve, and perfect the materials that stand between harm and those who face danger.